But let me do this first. Over the weekend, I finally got your syllabus updated, okay, and loaded on Blackboard. I got the research paper assignment and stuff updated and loaded on Blackboard. I got my locator card updated and loaded on Blackboard. I don't have it on my door yet. It's going there sometime when I can get a chance to print it off. I loaded the 10 pictures from Hubble telescope. Just they're fun. They're great pictures. They're out there on Blackboard. All of this is under content on Blackboard. Okay. And then the space objects in perspective. I've referred to that several times. A really nice little slideshow that's pretty fascinating. Worth a look there. And I got all of your chapter PowerPoints loaded. They weren't loaded before. They are loaded now. Every chapter we're likely to do has been loaded. I can't recall that there are any other videos that students have given me or I found that were helpful. It doesn't mean there's not some out there. But if you hear of some or see some or want to write on some, let me know. I'll review them. If they're good, I'll put them out there. Okay. But anyway, all that's done. So you can go to the website, the Blackboard, under content, under syllabus, and either print or copy me that page, that you've acknowledging that you've seen and heard and had opportunity to ask questions about the syllabus. Okay. That done. Here's what I wanted to find out. Okay. Last week, first day of class was Tuesday. We went over the syllabus. We went over the research paper. Emmanuel came in. Went over safety, and all that's recorded in that. Oh, the one other thing, I forgot this one. I also, the two classes that I recorded on the Screencast-O-Matic, which reminds me, yeah, I've started it, okay. Those are out there. Now, I created a new playlist for this class. It's called PHS111, and if you go to the bottom of the content is the very last entry, you'll see PHS111 YouTube videos. Click on that, you'll see those two videos pop up. You can go through, for those of you who weren't here on Tuesday of last week, you can hear everything and see most everything that went on in class. I tried to record as much as possible there. I didn't call the roll on class and that kind of on video. Okay. That is Coco, right? Okay, gotcha. So we did all that, and then we got started on chapter 14. Then a lot of you, or several of you, came in. Thursday was your first day, so you missed all that lead stuff, but you also missed the first part of 14. So if you do not feel ready for the test today, especially since I didn't have those YouTube videos uploaded until yesterday, if you need more time, you can certainly have it, any of you. But you'll need to come sometime during my office hours, which are amazingly few this term because I'm teaching so many classes. But you can come make up your test anytime during office hours. But let me briefly go through when my office hours are. On Mondays and Wednesdays, I have 45 minutes for lunch between 11:15 and 12. But you can come and do your test then if you want to. But I have a bigger chunk Monday, Wednesday, 3:15 until 5:15. 2 hours. You could come any of those times. Tuesday and Thursday, I have a reasonable chunk from 10:45 until this class starts at 12:30. That would probably be the most convenient time for you to do it. It's right before class. Or after class, that would be fine too. I'm here from 5 to 5:15 most days, but a lot of days I can stay later. Like today I can stay later. Thursday I can't stay later because I've got to somewhere I've got to be before a business closes in Homewood at 6. I got to be there, so I have to leave here about 5:15. So anyway, and then Fridays on the Birmingham campus, 7:45 till 1 o'clock. I extended my office hours on the Birmingham campus. But if you're going to come and make up a test then, be sure you tell me on Thursday that you're going to Birmingham on Friday so I can be sure I take the test with me, because otherwise it's going to be back here on Bestford. So if you are going to make up a test on Friday on the Birmingham campus, be sure you let me know on Thursday so I'll take it over there. So if any of you feel like you need more time for the Chapter 14 test, it'll be the last 30 minutes today, and we'll go with that. Now, the other issue was we didn't quite finish the lab that we were working on Thursday, partly because we had to change rooms right in the middle, and I think my phone's ringing. I'll be right back. You got it? Okay, I thought more steady state was in there, but I wasn't sure. Okay, so this is Terry, right? Okay. Did anyone else come in since I called roll? Okay. So the question is, how do we want to play things today? What we could do is finish the lab on Chapter 14 right at the beginning, and when we finish that lab, go back to 15, which we started last time, continue that up until we either run out of chapter or we get to be 4:30, okay, whichever, and then have the test from 4:30 to 5. The test is all multiple choice, 20 questions or fewer, so it's not going to take you long to do, but like I said, I can stay as long as you need me to stay today, but I usually allow 30 minutes, and then most people are finished before the 30 minutes is over. But that's the last 30 minutes today. What do you want to do now? Want to finish Chapter 14 lab, or would you rather continue with the lecture today? Say again? The lab? Finish the lab. Okay. Well, you've got your labs. All of you were here last time, weren't you? Anyone here today that was not here on Thursday? Okay. What's that? I know, but you got the lab that we're working on Thursday, right? Okay. Well, like I say, if you weren't here Tuesday and you feel like you need more time to study for the test, you don't have to take it the last 30 days. I mean, the last 30 minutes. 30 days. I don't know where I'm going. Okay, 30 days and 30 nights it rained. Okay. All right, so let's pick up with where we left off last time. I think there was only one person absent last time. I'll have to check on that. So we were on celestial coordinates. So we won't be doing Mercury right now. So let me back out of this slightly and get this one going. Okay. Okay. We had done question 1 on page 360 of the lab. We had done questions 2 and 3 on page 361. We had done 4, 5, and 6 on page 363. We had done questions 8 and 9 on page 364. And we had started working on the table, which is part of, they don't have, well, we were working on, we had done question 10, which involved filling out the table 47.1. Okay? That's where my memory has us ending. Well, no, we hadn't quite finished 10. Sorry about that. But we had done table 47.1. Is that correct? Yes. Everybody got that one completely finished. Okay, moving to 47.2, this is remember, we're moving to Altegard, Norway. By the way, I didn't bring up my globe. Let me run and get my globe. I'm going to put this on pause. Okay, Altegard, Norway. Any of you happen to know where it is? You do. Fantastic. Describe it.
It's like right near the Arctic Circle.
Just about as far north in Norway as you can get. They don't even have it over here, I don't think. But Norway is in Scandinavia, in the northern part of Europe. It goes all the way here and circles around, and actually has a very, very short border with Russia. Has a long border with Sweden, a little border with Finland, but even smaller with Russia. In fact, it was in the news recently. Altegard, Norway is somewhere up in the very uppermost. Now, it's inside a specific circle. Did you say what circle that was? The Arctic Circle. You're absolutely right. There's Arctic Circle. This is that black dashed line you see here. And a lot of northern Norway is above the Arctic Circle. Now, does anyone know what the Arctic Circle connotes? Say that again. Okay, yeah. Certainly you'll see the northern lights. You don't have to be inside the Arctic Circle. Sometime in northern Canada, well below the Arctic Circle, you can still see northern lights. I think there's been some recorded in New York and places like that, if the conditions are just right to see them. But yeah, you certainly will see them inside the Arctic Circle. But the Arctic Circle, remember, now you're the sun now, aren't you? Okay. I'm going to hold the Earth here, and you tell me, can you see that dashed line of the Arctic Circle right now? No, you can't, because it's always, the sun is always below its horizon when I'm facing this way, which would be dead winter, winter solstice. It's the shortest day of our year. They don't have any sunlight there, okay? So that's sort of a significance. Just giving something away, but anyway, that's the Arctic. That's Altegard, Norway. Its latitude is 70 degrees north. Okay, 70 degrees north, and here you see there's 0. Equator is 0, 15, 30, 45, 60. Then around 66, you have the Arctic Circle. That's not exactly close. And 70 would be somewhere north of the Arctic Circle. Okay. So, let's get our, now we don't have a celestial sphere globe, but it says readjust the position of the celestial pole to correspond to an observer in Altegard, Norway. So here you are. Oh, I need to turn this light back off. Easier to see the board here. Got to get my pen readjusted for, I can do black. Okay. Okay. Now, you're on Altegard, Norway at 70 degrees north. Okay. That's why I have to sit down to do this comfortably. So here's the globe. Okay. Now, you're standing at 70 degrees north. Okay. This is where you're standing right here. Okay. And you have on a big coat, you know, because it's cold up there. Okay. Altegard, Norway. Now, how do we indicate that? 70 degrees north, it's going to be something about like this. 20 more degrees, I don't even think I have it right. Let's try that again. Okay. Okay. There's your zenith, there's you. 7 degrees is going to be something like that. That's about right. So here is your 70 degrees north, or at least approximately. So therefore, your celestial equator, now that Carl's here, we weren't able to place the celestial equator until you got in here, okay. But, because you equilibrate everything. Okay, here's the zenith. Okay, let me get the, there's the celestial sphere, thereabouts, not drawn too well. Here is, what do we call this point right above us? Our zenith, okay? And we're in Altegard, Norway. If you want to move the globe, you can, okay? And the celestial equator is down here, along here, celestial equator. So this is 70 degrees north. That's where our zenith is over the celestial equator. Which means this down here is what? How many degrees? Second? 20, exactly. Here's 20 degrees. The celestial equator is 20 degrees off the southern horizon, okay? This is the northern horizon, which means, of course, the North Star is right here. Here's the pole star, Polaris, okay? Now, and that's another 20 degrees here, right? Because celestial equator to the North Star is 90 degrees, which means, of course, this over here is 70 degrees, which again reinforces, I'm not going to put north, I started to. The pole star never moves, right? Because it's right over our North Pole, so it stays in place. So whatever the altitude is of the North Star, that's our latitude of where you happen to be. Okay, and that sure enough is the case here. We proved that in the question 1. Just did it again. Okay. All right. I think that's what we need to for our setup here. Okay, do you have the first lab? Everybody has the first lab. Oh man, I didn't see you come in. Is it Brianna? Okay, did I pronounce it right? Okay. I have a student in an earlier class spelled the same way, but she's Brianna, and you're Brianna. Is that right? I keep getting the two crossed up. So y'all do this on purpose. I know you planned it ahead of time. All right, what the class decided to do, for those who just came in, is to finish the lab first, then go back to the class and work on chapter 15, and either before we run out of chapter 15 or run out of past 4:30, we'll stop and have the test on chapter 14. But if any of you don't feel prepared, I know last week was broken up, not everybody was here the first day. If you feel like you have more time, and by the way, everything's out on Blackboard now. The syllabus, the research paper instructions, my locator card, all the PowerPoints, the 10 Hubble telescope pictures that are just fantastic to look at. Nothing more than that. They're just pretty, really pretty. And Space Objects in Perspective, another real nice slideshow. I think you'll find interesting. And then I've got all the PowerPoints out there. Plus, the very last thing under content says Physical PHS111 YouTube videos. And there's where you can see the first class in all of its glory and the second class in all its glory. So if you want to go back and see any of that, you can. Okay. So you decide whether you want to take the test today or sometime during my office hours. I went over those again too. Monday and Wednesday, 11:15 to 12, and 3:15 to 5:15. Okay? And this is, help remind me, Dalen? No, Dalen. Oh, I marked you wrong. Okay. So you would be Terry, right? Okay. So I got you both here now. Okay. All right. So Monday, Wednesday, 11:15 to 12, and 3:15 to 5:15. Tuesday and Thursday, 10:45 to 12:30, and from the end of the class to 5:15, unless I don't have any obligations, I can stay later. Today I don't have any obligations. I could stay later, but Thursday I knew I've got to be in Homewood before 6 o'clock, so I have to leave by 5:15. Okay. And then Friday I'm on the Birmingham campus, 7:45 to 1. I changed those times to 1 o'clock in the afternoon. But if you are going to make up a test on Friday, be sure you tell me on Thursday so I'll know to take the test over there. Otherwise, I won't have it with me. Okay. Now, back to where we were. We're in Altegard, Norway. Very cold. Okay. 70 degrees north. And it says, fill in table 47.2, just like we did table 47.1. Okay. Now, the first thing in table 47.2 says on June the 21st, what is should be declination, DEC, of the sun. June 21st, what is the declination of the sun? Well, someone first tell me, what do we mean by declination of the sun? How high the sun is above the celestial equator. That's the declination of the sun. Okay? Now, on June 21st, how high is the sun above the celestial equator? Second. Okay, it says SEC is supposed to be DEC. On all three tables there, that's DEC. What is the declination of the sun on June 21st? Declination of the sun always is the elevation of the sun above the celestial equator. Now remember on our star chart, on June 21st, how high was the sun? Remember, that's the maximum it gets. It's hard to see, I know, here. With this dotted line here, that is the sun's path, okay? The ecliptic of the sun, and on June 21st, right about there, it's the very highest it can be. Does anyone remember what degrees that are? Hint. The angle that we're offset from vertical. 23.5 degrees, excellent. If you'll go up to the previous one, the declination of the sun is June 21st, is always the same no matter where you are. It wasn't that 23.5 degrees north, or plus 23.5 degrees, or 23 degrees 30 minutes. However you want to say it, that's the declination of the sun. And what is the definition of the declination? Above celestial equator. So you go another 23.5 degrees here, and here's the sun, Altegard, Norway, on June 21st. Okay, there it is. Okay, so we know the declination of the sun, 23.5 degrees. Now, the next question is the number of daylight, of hours of daylight of the sun on June 23rd. Here we'll have to sort of use our globe here. You're the sun again, right? Now, I'll do this for right now. Here's Altegard, Norway, somewhere here. Okay? Can you see it? Where my finger's pointing? Okay. As it spins, there it is at noontime. You're pretty high down. Can you still see it? Can you still see it? Okay, I'm low enough. Okay, here, because of the tilt here, it's inside the Arctic Circle. It never sets. The sun never sets because you're above the Arctic Circle. Down here in the Antarctic Circle, never comes up. Total darkness. But inside the Arctic Circle, the sun never sets. So how many hours of daylight? 24. Yeah.
Why they call
The midnight sun, the land of the midnight sun. Everything above the Arctic Circle in June 21st, the sun's up constantly. And the further north you are, the more days before June 21st than after June 21st. But if you're sitting right on the Arctic Circle, only June 21st is it. Exactly, the sun goes down and kisses the horizon but doesn't quite see. Above that, it'll do that, several days. But, June 21st, it doesn't even it stays off the sun. Yeah. That's why anything above there is called the land of the midnight sun. Yeah, absolutely. So how many hours of darkness? 0. How about December 21st? What's the declination of the sun then? Say again, minus 23.5 degrees. So this is 23 degrees, 30 minutes above celestial equator. This is the noonday sun at 21 June. Now, declination of the sun on December 21st is minus 23.5 degrees, which would be where? Below your horizon. I did it too much, but you see, let me turn this off again. I need a remote for the light. Okay. You see, now the sun is 23.5 degrees below the celestial equator. So that makes it 3.5 degrees down here. I threw it too big. But you see, it never comes up. So how many hours of sunlight do you have then? Daylight. 0. How many hours of darkness? 24. Very good. Y'all are catching it, okay? March 21st. What can you tell me? March 21st. We're tilted like this. You're the sun. Okay, do you see ultra-cardinal weight now? I don't know if you can or not. Not quite. No. But somewhere here you see it then, right? Okay? And you see it all the way around till it sets again. Which is, because we're like this, it's, what is March 21st, its name? Spring what? Vernal what? No, solstice is, it's what? Equinox. What does that stand for? Equal day, equal night. In German, night is Nacht. Equinox, equal night. All over the globe. 12 and 12. That's on March 21st to September 21st or thereabout. Okay? So what we got then? What was declination of the sun? We forgot that one. Oh, I forgot. Sorry. That was, no. Yeah, declination of the sun was 0. Hours of daylight? Hours of darkness? Excellent. Equal day, equal night. All right. Now we're going to move again. Boy, we don't stay still too long, do we? Now we're moving down to Quito, Ecuador. Okay, didn't we mention that before? What's the name Ecuador mean? Equator, yeah, it's named after the equator because it sits right across the equator. And Quito is just barely below the equator. So here they call it 0 degrees. And by the way, I'm reading a book that, long story, but the guy in the book is a travel, and they've just been diving in the Galapagos Islands, which are off the coast of Ecuador. An island group there, I think they're mostly volcanic islands, but a few of them may be coral, I don't know. But anyway, it's pretty fascinating. If there's one place in the world I would love to go before I kick the bucket, what we call it, the bucket list? Yeah, never mind. Okay, it would be Galapagos Islands. Anyone know what they're famous for? Ah, you're absolutely right. Darwin came up with his something of the species, evolution of the species, was that the name of it, or whatever he called it. But anyway, there are animals there on the Galapagos Islands that don't exist anywhere else on the world. And even those that do have changed and adapted to Galapagos where they didn't have to adapt that way anywhere else. There's also, off the coast of Africa, Madagascar has some very unique animals. That's a little bit closer, but the Galapagos Islands, they're a little bit further away. They are unique, and in fact, Australia has a few species that don't occur anywhere else. So you get these isolated islands, even in their continents, and sometimes species are there that didn't develop anywhere else. Okay, so now we're at Quito, Ecuador. Okay, now Quito, Ecuador, I've got to change some things around here, so let me do some erasing. Okay, North Star is not the same place. These certainly are not the same. That's not the same. My zenith is the same. I shouldn't have erased it. Okay, Quito, Ecuador. Okay, yeah. Were you the one that was looking for us at the, okay, yeah, we had to move, and the room they moved us to, another class was already in there, so we had to move here. So Brittany's here. All right. All right. Now, you don't have the first lab, so you'll have to take this one. Okay. And it leaves me with my old ragged copies of my original. No, I've got one more. So there's still one more person who hasn't been here yet. All right, and we're on next to the last page. We've just moved to Quito, Ecuador. Okay, I was in the process of correcting this. Okay, if we're at Quito, Ecuador, at 0 degrees on the equator, where is the equator for us, the celestial equator? Right above us. So our zenith is on the celestial equator. Okay? Because Quito, Ecuador is on the equator, 0 degrees. So where's the North Star? If we ever could see it, on the northern horizon, directly there, 0 degrees off of it, you know. Don't think we'll ever see it. We might, because it's not a very bright star, by the way. The North Star is. It's an important star, but not very bright. We won't say anything about students, okay? All right. Now, what's the declination of the sun? On June 21st. 23.5 degrees, it always is. No matter what day it is, on June 21st, it's always 23.5 degrees north. This is the sun on 21 June. Okay? Now, we're on the equator. 21 June. We're facing this way. Okay? Here is Quito, Ecuador. Okay? Somewhere here you see it, right? If the sun rises then, you see it all day long. My finger's still on. Somewhere there, somewhere, and then the sun sets. How long do you see it? On the equator, equal day, equal night. Everywhere on the equator, it's always 12 and 12. Okay? Always 12 and 12. June 21st, December 21st, September 21st, March 21st. Today is 12 and 12. In fact, I don't have anyone who's originally from South America or Africa here, do I? I had a student from Kenya. Kenya sits right, the equator goes almost smack through Kenya. And she said that was one of the strangest things she had to get used to when she moved here to the U.S. She thought every day was 12 hours of sunlight and 12 hours of darkness, because in Kenya, right on the equator, it is. There's no variation. The further north or south you get, the greater the variation gets. Okay? See, you right off the equator, it just changes a little bit. Here it changes more. There it changes big time. 12, 24 and 0 in Altegard, Norway. But on the equator, 12 and 12, 12 and 12, 12 and 12, whatever day. What's the declination of the sun on December 21st? Minus 23 and a half. What's number of daylight hours? 12. Darkness? 12. March 21st, declination of the sun? 0, because it's on the, yeah, that's what it is. March 21st, that's when the ecliptic crosses the celestial equator. So it's 0 then. And that's DEC rather than SEC, by the way. And the number of daylight hours are 12 and 12. You're on the equator. It never changes. Okay, any questions on overheated? Well, cool down, guy. Okay. We might be able to live without it for a while. I've not had that happen with one up here before. What I need to do is find the filter and clean it. Try to, oh, it's over there. What's that? It's either there or over here.
Probably all over it.
I got on that key in this one. That key in this one.
Those squirt things?
No, it's like, no, there it is.
Oh, really?
It's selling at the bookstore for like $4.
Okay.
You gotta buy air now.
What's that?
You have to buy air now.
Yeah. Yeah.
Well,
It looks like there's one there too. I don't know. Yeah, that's most likely because that's nearest the board. Okay, we'll leave it off for a while. Okay. Unfortunately, this room has no board. I can't draw on the board. But we're still recording. Now let's see. Oh, there it is. I'm afraid that was all question number 10. Okay, so you got to go back to 365. Okay? That was all question 10. We started off at 40 degrees north. I think. No. I think that's, where did we start? Is that where we live? What does the table say? No, at your latitude. And I probably didn't tell you what our latitude was, did I? No. 33 degrees. 23 minutes and 45 seconds, or either 15 seconds. I don't remember which. I'll have to go get the thing, but we didn't really need that, but we're okay. Because notice that didn't come into the picture anywhere here. Declination of the sun didn't depend on that. And we used the star chart, which used 40 degrees, yeah. Okay, no, that was all number 10. Then we went to Altegard, Norway. Then we went to Quito, Ecuador. That was all in number 10. Now we're moving to 11. Okay? What it says here is to calculate the altitude of the sun in degrees over the southern horizon at noon on the 21st of June for an observer at 40 degrees north. Okay? So I'm going to, you can't see what I'm doing now, but I'm just erasing Quito, Ecuador, except it didn't erase. Okay, let's try to get, yeah, now we're getting it to go. Okay. Okay. Now, what I think I'll do is turn on my projector again and hope that it's cooled down some. Okay. I think what y'all are talking about, that's what you sprayed through to clean the filters. Yeah, I know what you're talking about. But you have to take the filters out, otherwise you blow it into the light, and that's why you're trying to filter it out. So I still got to get up there and, or maybe have fiscal plant do it. Okay. Now, let me change that too. Okay. Now, what we're going to do here, you're at 40 degrees north. Okay, 40 degrees north means the celestial equator is 40 degrees from you. Okay, this is the equator. So the celestial equator is about like that, CE. And this again is 40 degrees north. You are 40 degrees north of the celestial equator. Now, the question is, you want to calculate the altitude of the sun in degrees over the southern horizon at noon. Well, first, what is the celestial equator above the southern horizon? 50 degrees. And where is the sun relative to the celestial equator on the 21st of June? Everywhere. 23.5 degrees north of the celestial equator. So it's going to be somewhere like there. 23 degrees, 30 minutes. Okay? Here is the sun. I drew a star. It is a star, but not that kind of star. Okay? Take that off of there and draw the sun there. Okay. Here is the sun at noon on 21st of June. Okay. So how far is the sun, where is the sun relative to your southern horizon then? Say again? Where is the sun, the altitude of the sun over or above the southern horizon at noon on June 21st? Here's the southern horizon here. 73.5 degrees, you got it. So that's 73 degrees, 30 minutes, or 73.5 degrees. That's where the sun is relative to your southern horizon if you're at 40 degrees north. Now here where we are, it wouldn't be quite that high because we are 33 degrees, 23 minutes, 45 seconds above the equator, so we're not 40. So, yeah. So I'm sorry, it'd be a little higher than that for us. Yeah, would be higher. All right, it then says number 12, repeat procedure 11 for December 21st. Where is the sun on December 21st if you're at 40 degrees? Where is the sun on December 21st? Negative 23. So let me see if I can space that. It's 23 degrees, 30 minutes south of the celestial equator. So where would it be over the southern horizon then? Okay, well, not quite. Subtract 23, 30 from the 50. You see, celestial equator is at 50. Subtract the 23.5 from there. Let's make that 49.60. Isn't that the same as 50? Okay, let's do that subtraction. What do you get? 26.30. So that's how far the sun is above the southern horizon on December 21st when you're at 40 degrees north. Make sense? Yay or nay? 26 degrees, 30 minutes, or 26.5 degrees, however you want to say it. It's still above the southern horizon, so it's positive, so it's up there, but it's not up there as far. So see how far it changed? 73.30, middle of summer, only 26.30, middle of winter. Okay, now, catch what's going on here. Think about this. the sun, every day from March the 21st, every day at noon, it's a little higher in the sky until June 21st, it's the highest peak. After that, it starts dropping every day. So what's it doing now? Down here was December 21st. Then it starts rising again. So at noon every day, the sun just a little bit higher in the sky at noon every day until March 21st. It'll be back here exactly our the complement of our latitude. Okay, I'll put it that way. Okay, and then it'll keep rising till June 21st, and then it starts going. So it just does this all year long, back and forth. And in the old days, the fear was that in the wintertime, it would get lower and lower and lower and lower and lower and lower, and they were afraid it was going to get below the horizon and never come back, and they'd be dead. But that's why they celebrated on the December 21st, the winter solstice, because the sun stopped going down and started going up again. Yay! We made it! Another year. Okay. They didn't know their astronomy, did they? For some reason, my chair is totally wrapped up in my power cord. So if I get trapped up here. Okay. All right, that was question 12. Now we turn to 366, which you've already done the tables on that, and let's go to number 13. Eratosthenes, I guess is how you say it, who lived in the 2nd century BC, before the Christian era, before Christ, was a Renaissance man before his time. Now, what do they mean by that? Yeah, he could do a lot of things. They say it next. He was an astronomer, a geographer, a historian, a mathematician, and a poet. Okay? He could do it all. Okay? That's what they called Renaissance men. But the Renaissance came much later. Do you remember what Renaissance stands for? Rebirth. Okay? So that's when the Enlightenment in Europe, which came. What's that? Oh, yes. Excellent. Okay. This was the rebirth, the Enlightenment in Europe. That's what we call the Renaissance. That came what? 1500s? Okay? This was 200 BC. Okay? A big 1700 years before our Renaissance in Europe. Okay? With such a diverse background, it is not surprising that he was the director of the greatest library on the globe at that time, which was in Alexandria, Egypt. You're absolutely right. In one of the scrolls in that library, Eratosthenes read that at noon on June 21st, in the southern frontier outpost of Syene, Egypt, way south in Egypt, here's Egypt, by the way, over here. And Alexandria was up there on the Mediterranean coast. And then there it is right there, Alexandria. And if you went down the Nile River here, down the Nile River, in very southernmost part of Egypt, one of the southern outposts there, Syene, Egypt, near the first cataract of the Nile. Now, I don't know exactly what that means. I assume it's like waterfalls or something like that. Okay. Okay. Right there, just about there, that at noon on June the 21st, I lost what I said here. Obelisk, you know those things like the Washington Monument to obelisk, a straight, tall tower, okay? Cast absolutely no shadow at all anywhere around. As noon approached, the shadows of the temple columns grew shorter and shorter until at noon they were gone. And even, reportedly, a reflection of the sun down in a well would come right back up at you. You could see the sun at the bottom of the well at noon on June 21st. So in other words, the sun was directly overhead. says use the celestial globe to determine the latitude of Syene, Egypt. Okay? Now, what we've got to do is kind of work backwards. Here we don't know the latitude, so I'm going to erase some of this. We don't know where the equator is yet, okay? But we do know where the sun is on June 21st. It's directly overhead. Let's take all this stuff out of here. I don't know why I'm saving my celestial sphere here. It's not that great of a sphere, but it just seems like it's easier to erase than otherwise. Okay. And where is the sun on June 21st relative to the celestial equator? 23.5 degrees north of it. So I'm going to make a guess now. It's right about there. 23 degrees, 30 minutes. Okay? So this would make this the celestial equator, right? Because here's the sun at Syene. I drew a star again. What's wrong with me? Don't answer that question. You don't have time. Okay. Here's your zenith. Okay. And this is the sun at noon on the 21st. 23.5 degrees above the celestial equator. You know it is. Everywhere it is. Okay? So that means the equator here is 23 degrees 30 minutes north. So what's his latitude? That's it. 23 degrees 30 minutes north. Does anyone happen to know what that latitude is? It has a name. Anyone know what it is? See if I can find it. See this dotted line right here? There's his name right there. Not a very pleasant sounding name, but okay. Goes across here, and there, sure enough, through southern Italy, not southern Egypt, very close to the Aswan Dam, which is that huge dam they built on the Nile River. And my guess they would have placed it right in the first cataract. Okay? That would have made sense. That's where the river is closer together before it spreads out. That would have been a good place for that. Anyone know what that dotted line is named? Those close enough that can read it. It's called the Tropic of Cancer. In the southern hemisphere, there's another one, 23.5 degrees south of the equator. That's the Tropic of Capricorn. You got it. So anything in between those two dotted lines, they're called the tropics. Equatorial areas of tropics. Tropical weather, tropical storms, tropic, that's where they come from. How much of the U.S. is below the Tropic of Cancer? Huh? No. All of Hawaii, and that's all. Florida comes close, but not quite. Cuba is right below it. And you know what is it, about 90 miles from Florida to Cuba, is that right? So we're, the tip of Florida, Key West, Florida, is about 90 miles north of the Tropic of Cancer. Okay? So that's where those names come from. And by the way, cancer wasn't a disease, it was a constellation. I don't know what the constellation stood for, but that's the one who, say again? Crab, that's it, okay. Okay, and the crab came up probably right around the 21st of March. That must be where it raised, that came above the horizon, so that's why it's called. Is that what? Is that the zodiac sign? Okay. That makes sense. And Capricorn, I'm guessing, is around the 21st of September. Am I guessing right? Anyone know Capricorn?
Capricorn is the end of December.
It's what?
End of December to
Okay, then I'm off on the one. What's that? Oh, okay. Let me turn this off again.
What's going on with it?
I think the filters must be clogged and the projector's overheating, and we could blow a bulb if we leave it on. See, the little sign said it's overheating. I have to do what it tells me. Okay. All right. So we did number 13. What is the latitude of Syene, Egypt? 23.5 degrees north, because it's Tropic of Cancer. Okay, readjust the celestial globe for your latitude. And before I tell you wrong, let me run up and get my thing. Before I do, let me turn this off. So we'll put this on pause. All right, we're back recording again. So I'm using Bessemer because that's where we happen to be right now. Bessemer here on the Alabama Atlas, and gazetteer, whatever you call it. Let's just call it 33 degrees, 23 minutes, 45 seconds. I remembered right. I can't believe I got those numbers right. So, readjust for our latitude, okay? So, okay. All right. All right. Now, let's see if perhaps this is cooled enough we can get a few more minutes out of it. Oops. Okay, folks. Evidently it's too hot still. What's that? Okay. No, I'm trying to turn it on. It's not coming on. I assume, I don't know if you can see it, that light is orange. I think it has to be green before it come on. So evidently it's hot still.
Put the water in.
What's that?
Put the water.
Okay. What? Stuff about War Eagle? No. Oh, okay, I didn't notice that. Okay. We need some, what you call it, dry ice, carbon dioxide, blow up there and cool it off. Okay. So unfortunately you can't see this, but you know what our arc looks like, our celestial sphere, right? Okay. Actually, I just thought of something I should think. Okay. Here we are. Number 14. Readjust the celestial globe. That's our celestial globe, by the way, for our latitude. And I just told you our latitude. What is it? Oops. That's not it. Okay. What is our latitude? Anyone jot that down while I was calling it out? There it is. I'm going right here. 33 degrees, 23 minutes, 45 seconds. Okay? So that means from our zenith, the celestial equator is 33 degrees, 23 minutes, 45 seconds. Okay? I may not have it quite done properly, but you get the general gist of it. Okay, that means the North Star is somewhere here. And this, by the way, here would be 33 degrees, 23 minutes, 45 seconds. Remember, that was question 1, proving that. Okay. which, what would this angle be?
33.
It's 90 degrees short of that one, right? No, 90 degrees minus that would be it. So rather than writing 90 degrees, I'm going to write 89 degrees, 59 minutes, and how many seconds? 60 seconds. That is 90 degrees, right? Because 60 seconds is 1 minute. That would make 60 minutes. 60 minutes would be 1 degree. Okay? Let's subtract from that 33 degrees, 23 minutes, and 45 seconds. Okay? What would that be?
That would be 56.
56 degrees.
36 seconds.
Minutes.
Minutes and
15 seconds, right?
yeah.
All right, 45 and 60. Okay. Not that we may need all that, but we've got it set up now. What range of declinations? What is a declination?
Degree of the sun on the
Okay, not just sun, anybody north of the celestial equator. Okay, that's the declination, measured from the celestial equator. So what range of declinations can stars have so that they never set? In other words, they're always above the horizon. Well, where would those stars be? Name one star that never sets for us. Polaris, the North Star. It never sets. It's always 33 degrees, 23 minutes, and 15 seconds above the northern horizon. Always. So in other words, all the stars within that band there, with that celestial, with that declination, okay? So this is 33, 23, 45 this way, 33, 23, 45 that way. So that would be, when you add those two together, what does that give you? Double this would be 66 degrees. When you double that, you get 90, which would be 30 with 1 left over. That would be 46 plus 1 is 47. Okay, that would be the lower declination, well, the lower angle. So the celestial equator is here. It's going up to there. Okay, we've got to figure out what that angle is. So it's 66. See, this is 33, 23, 45 above the northern horizon, right? That's where the North Star is. Its altitude above the northern horizon, always our latitude. We proved that earlier. So the stars that are within this thing, which is another 33, 23, 45 this way, because these stars go around the North Star, so that gives you this. So if we subtract this amount from 90, okay? So let's subtract that from 90. I keep bumping my elbow. Now what happened? My screen just went blank.
You X out of your slideshow.
Okay. There we go. Don't know why it did that, but it did. I guess when I bumped my elbow. Yeah. Okay. Powerful elbow there. Okay. It went 2 slides over. Okay. So let's subtract that from 90 degrees. But rather than 90, let's use 89 degrees, 59 minutes. Y'all see what we're doing? And 60 seconds. Okay, subtract that from, or the 66 thing from that, and what do you get? 23 degrees. Oh boy, this is come up familiar, isn't it? No, it's not. 12 minutes and 30 seconds. Okay. Not yet. Okay. That's this angle here. That's 23 degrees, 12 minutes, 30 seconds. Because this is 90 degrees here. We subtracted off the 66, so that gives you this. So what declination? From here to there, you add those two together. And what does that give you? It's 56 degrees, 36 minutes, 15 seconds. That's exactly what this is here. Okay? Amazing but true. That is what you get there. Okay? So that's where it begins, the declination from 56, 36, 15 to all the way down to here. What declination is that? That's 33 plus 90. So that's 123, 23, 45. Because this is your 33, 23, and then going to the horizon is another 90 degrees down. So just add 90 to that. 123, 23, 45. So that's your answer. From this one starts with declination 56, 36, 15 to 123 degrees, 23 minutes, 45 seconds. That range of declination from there to there. Okay? We got this one by adding these two together. That gave us this one. Okay? And then adding 90 degrees to this, that gave us this one. Okay? It is hot in here. What I've seen some of the other classrooms doing is opening windows. I don't know if it's hotter outside or in. Y'all have a guess?
I've got the time.
What's that? Okay. Let's see. I think it's hotter outside, but at least it has a breeze. Y'all have a breeze. Huh? It really is. The secretary at work said Friday, we had all 4 seasons last week. Yeah, the bottom one is 123, 23, 45. You just add 90 to this one.
Okay, what's the line to 56, 34?
This one here is these two added together, which is 56, 36, 14. So this is the range from this to that. There's your declination of the lowest stars in the sky up to those. So basically all the stars in between them. In reality, you could just say from here to 90 because all those stars are still in there, but that covers the whole range. Okay? Stars with those declinations. Is that any better or worse? Y'all like having that wind or not?
I think it's better.
Okay, I do too, but I shouldn't have on the flannel shirt today. I don't know what's wrong with me. It's January, okay? All right, so finally we finished number 14. Now, I don't have the up-to-date information on Mercury and Venus. So we're going to use the previous year when I did have the information, and we're going to answer the next few questions. Okay? Now, everybody understand Mercury and Venus? This actually goes into some of the stuff we talked about in chapter 15. Where do Mercury and Venus sit relative to us? Yes, they're closer to the sun than us. So guess what? Wherever the sun is, somewhere pretty close to the sun is Mercury. So Mercury's revolving around the sun right out there right now, but we can't see it because the sun's way too bright and Mercury's way too dim. Yeah, it's reflecting off the sun. So it's somewhere there. Venus, by the way, is also somewhere there around the sun. I don't know if it's completely up now, but it's probably pretty close. So here is the question. When is Mercury visible in the dark sky And I'm going to use this from an earlier year. I don't know if it's anywhere close to true, but let's see. All right. It says here, in this one that we happen to be I'm looking at here, says Mercury is visible in the early morning sky. So that would be just what? Before sunrise, just before sunrise. Why wouldn't it be visible after sunrise? The sun bleeds it out. You can't see it because the sun's so bright. So if you could see it, it's going to be, if it just happens to be revolving around the sun above our horizon, we might be able to see it then just before the sun comes up. As soon as the sun comes up, it's gone. Okay? Venus. Where is Venus visible in a dark sky? It says here, Venus is low at dawn near the east-southeastern horizon. So when is that? That, again, would be just before sunrise. Okay? Okay. Venus has two names, the morning star or the evening star. Because when the sun sets, it could be that Venus is trailing it, and we see it then. So we'll either see Venus in the morning or in the evening or not at all. Mercury, most of the time, not at all. But if you ever see it, it's not going to be long. So the answer to the next question, number 17, estimate how long each is visible in the dark sky. Mercury, I'll guarantee you, if it is visible, it's only going to be a number of minutes, a few minutes. That's your only shot at seeing Mercury, either just before the sun comes up or just after it's set, and then you might not see it either time anyway. Okay? There's a couple of reasons. Number one, Mercury is so tiny. It's a small, small planet. And number two, it's so close to the sun, either the dusk or the dawn's going to bleed it out really fast. So you're never going to see it for more than a few minutes. Venus, on the other hand, you might see for a few hours, but never many hours, just a few hours. Okay? Those are good estimates. And again, you'll either see Venus in the morning or in the evening or neither. Okay? So, that finishes today's lab. Okay? What's the question? Just a few, no more than a few hours. Okay? Never as many as 12. Never going to be 12 hours. It'll always be fewer than that. Quite a few fewer, usually. Only 1 to 2, maybe up to 3 hours. I don't know exactly. Okay, if you're finished your lab, you can turn them in today. If you want to take it home and fiddle with it, you can. Especially for those of you who weren't here for the whole time, I've recorded everything I could on the lab, so you'll be able to get it. Now, we don't use Integrity anymore. We're using what they call Screencast-O-Matic. Okay? It's cheap. Yeah. No, here's what you have to do. Anyone else new here? Okay. When you go to Blackboard, you know, in this class of Blackboard, the upper left corner, there's a bunch of tabs. Content. That's where everything is here. The syllabus is there now. The directions from the research paper, remember those? Okay. My locator card is there. I've got 10 beautiful pictures taken by the Hubble Space Telescope, just for fun to look at. There's Space Objects in Perspective. Really neat little slideshow. I think you'll find that interesting. Then there are the PowerPoints for all the chapters we're going to cover. And then there is, it says PHS111 YouTube videos. That's where the first two classes are.
Oh.
Okay.
So
Now, on YouTube. It's on YouTube, yeah. Okay. But there is a link to the actual playlist, so you see just those two. Okay. And you click on either one to see them. Okay, now, here's the sad news, though. As soon as this class is over with, I start uploading. But Integrity used to upload within half hour, 45 minutes, certainly within that. Sometimes long classes in the lab might be a little long. This one takes hours. So I will upload it, like today, I'll leave it in my office uploading overnight. Last time, it didn't finish uploading before my computer went to sleep. So I had to upload the next day, so I can't tell you when it'll be uploaded. But even when it's uploaded, I still then have to send it to the playlist. So it's going to be a few days, whereas Integrity was just a few hours. This is going to be a day or two. Okay. Sometimes it'll be a few hours, but that's it. So, okay, you ready for it? All right, good deal. If you want to turn it in now, you can. It's up to you. And by the way, I just wanted to say something, not putting any pressure or competition or anything, but I've received 2 papers already this term. Not from mini-term classes either, full-term classes. Y'all are a mini-term. Guess what? It's even more important for you to get the papers in early. You have half the time to do it as the other people.
We're doing another paper thing?
What's that?
We're doing another paper?
Oh, yeah.
Okay.
The research paper instructions are there on Blackboard. Also on the first day of class, you can hear me talking about it. Same thing you've heard before. Okay. All right. Good deal. Give me. What's that?
You didn't talk about it yesterday, I guess.
Or Thursday. I can't remember if I forgot to mention it or not. Okay. Now, what we'll do now is move back to, let's get this over with. Okay. Thank you. Was there a question or something? We could. That means we'll just continue till 5 o'clock today in lecture. Is that what you want?
So this Thursday we have a testing class.
Huh?
This Thursday we have a testing.
Well, we were supposed to have it today, the last 30 minutes, but I was telling people, if you weren't ready, because some people weren't here Tuesday of last week, and some weren't here Tuesday or Thursday of last week. So if you needed more time, you certainly could have it. But now the question is, can we have it then? We're going to continue with chapter 15, and the test is on 14. If y'all are okay with that, I'm okay with it.
See, I can't even find my book because the library.
The bookstore?
The bookstore.
They ran out?
They were out when I went up there to try to buy them.
Okay.
Like, I don't have the book. And I
Did you go to this library? I mean, bookstore? Or
Yeah,
what?
this.
Okay. Wow. Has anyone else not been able to get a book? Did someone get the last one on the shelf?
You can get them off Amazon too.
You can. I loaned one to somebody early in the term. I loaned one to someone early in the term. Is that person here? Because somebody left me one. I said you can contact this person if you want to buy it from them or not. Okay? That wasn't anyone who's here. Seemed like it was a guy, but I guess we could be missing somebody.
So, did we decide what we were going to do? Just push the test like Thursday? Anybody?
Huh?
Is that what we decided we were going to do? We're going to push it Thursday?
It's fine with me. If y'all want to do that, we'll just continue till 5 today with
I mean, that's good.
class.
They can take it. I can't take it.
Okay.
That gives everybody plenty of time to, get their study.
They wanted to.
But now, when is our chapter 15 testing?
I don't think we'll finish 15 today. If we do, then it'll be back to back on Friday, on Thursday, but we'll see. I don't think we're going to finish it today. We got too much to go.
So we'll push 15 back to Tuesday. 14 will be Thursday.
Yeah, that's what it looks like. Yeah.
So y'all done for calls? Anybody? Any objections? Nobody?
Okay. Our auctioneer is here. Okay. 51, 53, go. Okay, good.
So,
Thursday.
Okay. Everything's getting off.
So we're staying
Okay.
till 5.
What's that?
We're staying till 5.
yeah.
I don't want to cheat you out of a penny of your tuition dollars. You should know that. Right? You remember, don't you? Okay. Somehow I moved the my marker, but I think this is where we left off last time with Mercury.
Picture's missing out of your slide.
What's that?
Picture's missing out of your slide.
The picture, what?
Picture of the planet's missing out of the slide.
Is it?
Yeah, look.
Okay.
Behind you.
Second? I don't know what
Picture
you're...
of the planet on the slide's missing.
Okay. You mean that one?
No, it had like a picture marker right next to it.
Oh, yeah. It'll gonna come up next.
Okay.
Okay. Yeah. This is, yeah. In the book, you have a pretty picture of Mercury. I think it's coming up in a minute. Okay. Now, let's talk about Mercury. Already it's been mentioned today, it's the innermost planet, the one closest to the sun. Which means what? You might think it's the hottest. And certainly at the peak of its temperature, it is the hottest. But, okay, and when would be the peak of its temperature? When it's turned toward the sun, right? It's noonday. Yeah, it's burning hot then. But then, too, when it's nighttime on Mercury, it is really cold. Not colder than some of the others, but very cold. There's a reason for that. The huge swing in temperatures. Anyone know what it might be? No atmosphere. The atmosphere, basically our atmosphere is our temperature moderator. Okay? I think you may have noticed, if you haven't, start noticing. On a cloudless night, it's usually going to be your coldest night, your coolest night. On a cloudy night, it's not going to get as cool because the clouds sort of act as a blanket for us. You know, our atmosphere acts as a blanket. So on average, the hottest planet is actually Venus, because Venus has a very thick, dense, messy atmosphere, mostly carbon dioxide. What is carbon dioxide? It has a name that people have been talking about a lot these days.
Greenhouse.
A greenhouse gas, you got it right. It doesn't let the heat back out, okay, as easily as oxygen and nitrogen does. So it's a greenhouse gas. That's why we think our temperatures are increasing, because we're increasing our CO2 levels in our atmosphere. And we think that's coming from human interference rather than just the natural cycle. Okay? It's happened before on the natural cycle. It's happening much faster now because carbon dioxide is a greenhouse gas, and that is the majority gas on Venus. But we're not on Venus yet. We're on Mercury. So its innermost planet, it's a highly elliptical orbit. Remember, most of the orbits are fairly close to circular. Mercury is one of the most elliptical of them. They're always slightly elliptical. It's highly elliptical. Not as highly elliptical as Pluto was, but Pluto is no longer a planet. It's a dwarf planet. Okay? The average distance from the sun, that's why we say average, because highly elliptical orbit, sometimes it's further, sometimes it's closer, is about 4/10 of Auburn University, right? No, what does that mean? AU? Astronomical unit. What is an astronomical unit? It really should be a solar unit, because we don't use them in the rest of astronomy. We only use... Yes, it's the average distance between the Earth and the Sun is 1 astronomical unit. So if you had the Sun here and us here, it'd be about 4/10 of the way between the Sun and us. Okay? Now, I'm pretty sure that's measured from the surface of the Sun. Probably doesn't matter that much, except Mercury's so close, I don't think it would be from the center of the Sun. Okay? The orbital period, we mentioned this when we looked at the table, and for those who weren't here, and she stepped out, so I'll say it again. That table that's on the next page, page 382, or somewhere thereabout, wonderful table to look at. Lots and lots and lots of very valuable information. But the orbital period of Mercury is about 3 months. So our orbital period is what? 1 year, 12 months. So it goes around 4 times for every one of ours. But the strange thing is, its rotational period, the spin cycle on it, is, how much is ours? I'll get it. one day, which is 24 hours, what is it? It's 59 days, 2 months, okay? Almost 2 months is to spin once. So its orbital period is 3 months. Its rotational, its day, you might say, is 2 months. So its year is 3 months and its day is 2 months. So there's only what? 1.5 days in a year or something in their year, okay? It's rather slow spinning but fast rotating. All right, and as we just said, visible shortly, only a number of minutes, either after sunset or before sunrise when it's visible. Quite often it's not visible at all. When it is, shortly after sunset or shortly before sunrise for just a few minutes. Highly cratered, why do we say that? Say again? Been hit by a lot of asteroids, meteors, space junk, everything. And why does it get cratered? Because it has no atmosphere to slow it down. So our atmosphere is our blanket, but the atmosphere is also our protector. Because when a piece of rock from space, asteroid, meteor, part of a comet, whatever it is, enters our atmosphere, most of the time it burns up in transit through the atmosphere. What do we call those? Meteorite. Okay, it's a meteorite if it lands on the surface of the Earth. It's a meteor if we see it up there, so all meteorites were one time meteors. But it's also, what is the common name for it? Shooting star or falling stars, okay? That's what we're seeing. It's not a star falling. It's a piece of junk burning up in our atmosphere. If it's big enough and doesn't burn it completely up and lands on the Earth, we call it a meteorite, okay? No atmosphere to slow them down, to do anything. Everything that comes within range of Mercury hits Mercury. So it's highly, highly cratered. And guess what? All that stuff is doing what? Going around the sun. Where is Mercury? Right next to the sun. So it's going to get pelted, more than we would. We're further out from the sun, so we only intersect a little bit of that. It gets a lot. It is by far the smallest planet. Now, when Pluto was counted a planet, Pluto was smaller, but it's no longer a planet, so that makes Mercury the smallest planet. How small is it? It's just slightly larger than our moon. It's actually smaller, I think, than 1 or 2 of Jupiter's moon and 1 of Saturn's moons. So it's actually a really small planet, okay? The smallest of the planets. Okay, now this shows why we say that it's hard to see Mercury, okay? And this is not, they've blown up this figure, okay? But here we are on the Earth, and when the sun is either just peaking up or just going down, Mercury is so close to the sun, okay? Now this is strange but true. When it's closest to us, it's almost impossible to see because the face of Mercury being lit by the sun is facing the sun, okay? So we only see a little bit of it there. What's the chance of that? In the few minutes we have to get that little sliver, a new Mercury. It just doesn't happen often. When it's over here at equidistance from us and the sun approximately, we only see about half of Mercury. So it's still hard to see. When we get a full Mercury, it's on the other side of the sun. And so that's where we would see it if we could see it at all. So, but then it's further away, so it looks smaller. So there's not much of a chance. And by the way, this is not particularly scaled well. If we had that much curvature, the radius of Mercury would be so small, so they highlighted this. Now, of course, if Mercury happened to be down here before the sun rose or after the sun set, you ain't going to see it at all. So most of the time, there's a good chance you'll not see Mercury. Very little chance you'll see it just a few minutes before sunrise or a few minutes after sun sets, if you can see it at all. It's such a small planet and so close to the sun. It's not up there for long. When it's closest to us, it's the smallest area visible. When it's farthest from us, the most area is visible, but it's so small, far from us, it looks so small. So yeah, it's not going to see Mercury very often, if at all. I'm not sure I've ever seen Mercury and known it was Mercury. Okay, and this is a picture of Mercury. If you are in your book, is this the one you were thinking of?
Yeah.
Yeah, that's the picture of Mercury, and you can see it is cottage cheese. I mean, it's just pelted with craters all over the place. Big craters, little craters all over. It's terrible because no atmosphere to slow down the space rocks that are out there, so they just crash into it like crazy. That's Mercury. The side that's facing the sun, extraordinarily hot. The side away from the sun, really, really cold. Okay? So, that's Mercury. On average, it's a hot planet. Closest to the sun, when it's noonday there, it's the hottest any of the planets. But on average, Venus is actually hottest. So here's Venus. Okay? Sun, Earth, what do we call that distance? Sun to Earth? Astronomical unit. 1 astronomical unit. Mercury's about 4/10, Venus about 7/10. Okay? So Venus is closer to us than Mercury is to the sun. So it's our closest neighbor of the planets. The moon's our closest neighbor. Okay, 7/10 of astronomical units. It's either, as you said, the morning or the evening star. It's not a star, but it's the brightest thing out there. If it's visible, it's the brightest thing out there, either in the early morning or in the late evening, the early evening. Okay, right before the sun comes up or right after sun sets. One or the other, sometimes neither, but you'll never see them on both. Now, it also exhibits phases a lot like the moon, depending on where it is. If it's closest to the Earth, we'll have a new Venus. You hardly see any of it at all, just a little sliver. If it's on the opposite side of the sun, you get a full Venus. But it's close enough, that's really bright, okay? But it would have to be after the sun set, you'd have a full Venus, okay? But it's generally the brightest star. It's the first star you'd see in the last star you would see in the morning, first star you would see in the evening. And it's not a star, it's a planet. That's why we call it the morning or evening star. Now, only 2 planets have this characteristic. Okay. And one in particular is Venus. The rotational motion is opposite its orbital motion. Okay? Most of us rotate and revolve the same way. Well, it revolves the same way around the Earth, around the sun, but it rotates backwards. Now, there's one other planet that does that. That's Uranus, but it's much slower. Venus, goodness gracious, the Venusian day, its one rotation is actually longer than its trip around the sun. So it's spinning so slowly, backwards, by the way, but it goes around the sun one time before it spins one time. So its year is longer than its day. Okay? Now, the last time we were at the planetarium at Sanford, Mr. Weigel was saying, I think it was the last time, there are some theories out there that think Venus may have been hit by something really big and really hard that made it spin backwards. But it's spinning so slowly backwards. But that was the idea. And I asked him at the time, and he wasn't sure, but he said it's a pretty good guess. It may have been, there's also a theory that the moon was really once part of the Earth, and we got collided really hard, and that knocked the moon off from us, but it was such a hot, messy thing that we both evened up, but the moon became spherical, and we went back to being near spherical again. So, but that's us. I wondered if that was the same time frame, and he didn't know. That's interesting. Okay, because it's the closest planet to us, it's been visited by probably more probes than any other planet. Second would be Mars, which is the next closest. But one of the problems that Venus has, as I mentioned before, it's so incredibly hot. I mean, it's incredibly hot. Okay, so we can send probes out there, but the heat, they're not going to make it to the surface. If they did, they're probably going to deteriorate, because in addition to carbon dioxide in its atmosphere, it also has a lot of sulfuric acid, which is not really good for, electronic devices to be in sulfuric acid. So it's not a very pleasant place to be. When they say women are from Venus, men are from Mars, I wonder how, never mind, I won't go into that. Okay, we won't say that, will we? Okay. Now, numerous probes. In the text, it may show, let's see, it may show up now. Yeah, here they are. Here's a listing of some of them. All right, now, if you glance at that, what do you notice first? What's one of the first things that pops out at you when you look at that table?
It all started during the space race.
That what?
It started about the time of the space race.
Yeah. Shortly after we got out into space, who did it? Yeah, Soviet Union went there first and seems to have gone there most often. Okay? And because they did that, we decided we'd go to Mars then, because we weren't going to be beat by them, so we're going to go to another, and we'll beat them. So I'm not sure that was the thought, but who knows? I don't know. So anyway, USSR has sent a lot. Okay, we've sent several. Mariner. Sounds like that was going to Mars, wasn't it? It may have been, but it went by Venus first. There's another Mariner that did. Pioneer, a couple Pioneers went through, several did. Actually, Pioneer 13 went twice. That's the same thing, I guess. Okay. And then we sent Magellan and Galileo. I think Magellan went somewhere else anyway. Galileo may have gone somewhere. It just, when they flew by, that means it took pictures, it took measurements and stuff, but it was on its way to somewhere else. Now, sometimes it might fly by and just hang around a few trips, because what they do, it's really interesting how they plan space travel. What they'll do is go around a planet and circle, but not really a circle, elliptical orbits. And when you go on ellipse, you're slower when you're further away, and you go faster when you're close. That's what we do around the sun. That's what comets do around the sun. Real fast around the sun here, very slow when they're way out there. Okay, so I forgot to tell y'all. Sorry about my voice. I went to a basketball game Saturday night. I yelled too much. Sorry, but my wife yells at me. Okay. Anyway, that's what they do sometimes with the flybys. They're going to loop around Mars a few times and get the slingshot effect and let them sling us out. It saves on fuel. It uses their gravitational field to sling us out. It's an interesting concept, but it's done. So some of these were on the way somewhere else and just happened to go by Venus and get a slingshot. Okay. Boy, to figure all that out, you talk about some deep math, because these planets are way, way apart, and in different parts of their orbits and stuff, they have to do these calculations really precisely. It's amazing to me they can do it. Okay. Mostly CO2, carbon dioxide atmosphere. Okay. Very, very high temperatures, and because it's a very thick, dense atmosphere, very high pressure. Do we have any pressure on us right now? Do you? Any pressure? Early in the term, y'all have any? No, I'm not that kind of pressure. Okay, yeah. Our atmosphere is heavy enough that we're getting hit with 14.7 pounds for every square inch. A square inch is about your two thumbnails together. Is that right? Yeah. Not thumbnails, your thumb joint. Because that's about an inch, and that's about 1 square inch. And think about how many square inches are on your body. Multiply that by 15. That's a lot of weight on you.
Is that why people can jump higher on the moon or something?
Yes, that's exactly it. The moon has much less, well, two reasons. It has less gravitational to hold them down, but no atmosphere, and the moon doesn't. So yeah, They have no resistance, except for the gravitational resistance. So yeah, we have a lot of pressure on us. Why aren't we crushed? Because our body's pushing out with 14.7 pounds per square inch, or maybe even a little bit more. That's why when you cut yourself, the blood comes out rather than goes in. You have a little more pressure inside. Now, my mother used to do this, and it was really strange, and I hate that I can do it now. Don't pull up on skin. Number one, there's an awful lot of skin to be able to pull up on, but then when I release it, see how long it takes to go down? If y'all young people do that, it goes right down. You have better turgor pressure than I do. I'm getting old. The valves don't work as well, that kind of stuff. She had a teepee that stood there for a while before hers went down. But anyway, so they have even greater pressure than we do. I'm guessing 20, 25, 30, maybe even more PSI, pounds per square inch. We would be crushed there. We'd be dead because we can't live in carbon dioxide. We can't live in those temperatures. There's nothing about Venus that would be attractive. No way we're ever going to colonize Venus. Okay. Now, the surface is mostly flat but varied. It has some volcanoes. It has some other things. In fact, it seems like they say one of Venus's volcanoes is taller than any mountain on Earth, Mount Everest even. So I don't know how they say mostly flat, except they don't have as much range of topography as we do. Okay, we've been there many times. All right, there is one of those volcanic mountains there. Now, we did get a probe close enough that lasted long enough to take a picture. It's an image from 8-kilometer or 5-mile high volcano on the surface of Venus. Mount Everest, anyone know how tall that is? Seems like it's 60-some thousand feet, but a mile is, I'd say it may be, this one may not be as tall as Everest, but it's still pretty tall, okay. The image was created by a computer using Magellan. Oh, it doesn't have that anymore. One of the latest things we did. By the way, in your book, some of the books, if you have the newer editions, it goes beyond that last slide. This last slide ends about 1989. Okay? There are two more since then. One of them from ESA. I don't see ESA anywhere on there. What is ESA? European Space Agency. They are now involved in this stuff. In fact, we collaborate with them a lot. They actually were the sponsors for that one. And Messenger then was U.S. There was Magellan. Next to the last one here, fourth from the last in your book. Okay? That was the one. The image was created by a computer using Magellan radar data, simulating the viewpoint of elevation. So they didn't actually get down to the surface. They'd have been burned up by then. But they did the radar, and then the computer imaged it down there as if you're looking from the surface. These things that look like the simulated colors are based on color images recorded by the Soviet Venera 13 and 14. That was these two. So they actually back in '81 got some. They did have a lander with some and sent some photos. Both of those landers did. They didn't last very long. It was so hot, such a corrosive, miserable environment there. They couldn't last long, but they did send some photos. Okay. And this is based on that. More than likely, these things you see here are molten rock. It's that hot, okay? And this actually looks like lava that has recently solidified. It's a very inhospitable place, to put it mildly. And by the way, that dense, thick atmosphere doesn't let much heat go out at night. Remember, it doesn't spin very fast, very slow in fact, but the whole surface temperature stays about the same because the whole planet is hot, okay? And the atmosphere is a big blanket that keeps it hot. I'm sure there's some variation, but it's not a lot. So on average, it's hotter than Mercury, I think. But certainly Mercury at this peak is hotter. So let's move on to Mars. We're skipping Earth. Did you notice that? But we're going to cover Earth in the next chapter. So we'll get there next. So let's go to Mars now. So here's the Sun. Here's the Earth. 0.4, Mercury. 0.7, Venus. 1.5. That's another halfway between us and the Sun. Another that much beyond Earth. So it's further away from us than Venus by quite a bit, but not as far as it is from 0.6 from us to Mercury. So it's just 0.5 beyond that. So it's not much further away from us than it's a little closer than Mercury is to us. Okay, so that's its orbital distance. It's geologically active regions, which means there's things going on, okay? Or at least they have been going on in the past. The volcanoes that we see there and looked at, see, so far they're all inactive since we've been looking at them. So we think they're probably fairly stable. There are canyons. Now, what are canyons usually caused by here on Earth? Water erosion. If you see canyons on the surface of Mars, that suggests that there may have been flowing water at one time. Is there now? None detected at all. Well, I won't say it all. We'll get to that. Now, there's also what they call terrace plateaus, mostly near the poles. And now remember, Mars is further out than we are, so it's colder, okay? And you have these terrace plateaus at the poles, which would be the coldest part of that. So that could suggest ice flow, as in glacier movement and stuff, terrace plateaus. Maybe. We don't know that. It's just suggestion. None there now. The flat regions are pitted with craters, like, well, no, that's not quite that. That, I think, is where a lander landed and made that. But the flat portion, you do see pitted. And when you say pitted with craters, what does that suggest to you? Second, it's getting hit by stuff. And why is it hit by stuff? It has an atmosphere, but it's very thin. So it doesn't slow them down much, so it gets hit a lot more than we do. And its atmosphere is mostly CO2, carbon dioxide, which would be not very hospitable to life, in fact, inhospitable. Now, Mercury, no atmosphere. Venus, CO2. Earth, oxygen and nitrogen, with a little CO2. Mars with CO2. Why would we have no CO2 on us? So we have some, but it's not very much. We have green plants, and what do green plants do? They absorb CO2 and give off oxygen. Oxygen is a very reactive element. So guess what? It's going to combine with something unless something is producing it. Thank you, plants. Without plants, we're not here. Nowhere close to being here. We'd probably be a largely CO2 atmosphere, just like Mercury, Venus, and Mars, with no life. So I think, I don't know if this is true. Now, where does nitrogen come from? I can't answer that one. But I can say it's thank you, plants, for cutting down our CO2 atmosphere and increasing our oxygen. Yes?
I heard somewhere Mars is the oldest planet in the solar system. Is that true?
I don't know. Most of the solar system was, we'll get to that in the next chapter. No, it's at the later part in this chapter, maybe later today, but I doubt it. When our sun was going through that turbulent period, remember we talked about star formation last time, you know, it attracts the gases, they get hotter because more gravitational thing, until they get so hot, nuclear fusion happens, and they blow up, you know, sending things way out there. But then the gravity pulls them back, it goes back and forth a while. It's not an instantaneous process. So I think one of those big blow-ups that it had, it sent stuff out into its outer regions. So I would have thought most of the planets would have probably formed about the same time. Now, maybe for some reason, Mars may have cooled a little faster. I can't see why, but it's rocky. So it's the furthest out rocky planet, so maybe it cooled faster, so maybe it formed to be what we see it today sooner than the other terrestrial planets. The gas giants, they took their time. They did whatever they were going to do. So maybe that's the reason. But it won't be by much, I don't think. Just a few million years. What's that among friends, you know? Okay. All right. I don't know. I'm making it up. Okay. Thin atmosphere, mostly CO2. Strong evidence for liquid water in the past. Canyons and terraces. That was sort of suggested. But we don't detect any liquid water now. There seems to be ice under the surface near the poles. And there's some reason to think there may be subterranean water, maybe deeper in, like our aquifers, underneath the surface. It seems like there could be some lakes and things under there, but frankly, it seems like it'd be so cold, they would be ice. But if they're real close to the core would be warmer, and maybe it's melted water. I don't know. I don't know if there's any good evidence that way or not. Okay. So, numerous space probes. Let's see if we have one. Oh, yeah, let's see. Here's sort of what they're talking about by the canyons and the terraces and other things. When you look at some of these pictures, and we've gotten really close, see Mars with not much of an atmosphere, and it's not as nasty and hot as Venus is, so you can get closer. I mean, we've got probes out there that are still running around, rolling around out there. It's not a bad atmosphere to live in. Couldn't happen on Venus, okay? But it can on Mars. And some of the pictures I've taken, you can see that's a rock with a shadow, because the sun's shining and stuff like this. But here we have angular, I can't read that. It looks like uncertainty. What does that say?
Unconformity.
Say again? Unconformity. Yeah, that's what it is. Strange word. I would think nonconformity, but unconformity. Patinique or patink or something like that. Anyway, it almost looks like there's residual, sedimentary rocks. How do sedimentary rocks happen except underwater? Okay, sediments out. Okay, so and you can see these layers here. There's one. It looks like there could have been. Oh, that's this thing. Okay, it looks like there's some evidence, strong evidence for liquid water in the past. We don't know. We weren't there. Now, what do we call Mars? The red planet. Why do you reckon that? It's red, and that's iron oxides are red. Okay, so that's probably, most of our solar system, like the Earth, mostly iron. Not on the surface, but deep down, most of us are iron. Probably the same true for Mercury and all the terrestrial planets. So it's oxides of iron are red. Okay. Now, they didn't show the tables, but when you look at table 15.3 in your book, you'll see that ours outnumbers Russian, not by much, but a little bit. And then, of course, ESA, European Space Agency, has a few now. A few of these tables you might see RSA, that would be the Russian Space Agency after the Soviet Union split apart. So USSR is Russia, but it was Soviet Union. RSA would be Russia. Okay. And this is not completely up to date, but it's pretty much, we've landed on Mars. We've got surface rovers out there. Spirit and Opportunity are two that are out there. I think now there may yet be another one. Pathfinder, I guess, was one that was there earlier. Okay. But anyway, we know more about Mars than we probably do any other planet. Okay. So, not at all. Okay, yeah, that'll be fine. Okay. Let's move on to Jupiter. Okay, let's get our bearings again. The sun's here. 4/10 of an astronomical unit is Mercury. 7/10 is Venus. 1 astronomical unit is us. 1.5 astronomical units is Mars. 5 astronomical units. 5 times as far as we are from the sun before you hit Jupiter. That's a big gap there, from 1.5 to 5. Whereas the rest of them were less than 1 apart. This one's 3.5 times further out. What's in between Mars and Jupiter? The asteroid belt. Many think that should have been another planet. They think that maybe Jupiter, being the most massive planet by a big margin, by the way, too, 318 times our mass. Okay, we think we're big? 318 times our mass. That's Jupiter's mass. We're bigger than Venus, we're bigger than Mars, we're bigger than Mercury, surely. Jupiter, 318 times what we are. It's mostly helium and hydrogen. Now, where do we get those? Where have we heard of hydrogen and helium before? What? Yeah, they're in the periodic table for sure. But what other bodies were we talking about?
They usually make up stars.
That makes up stars, including our sun. So here's the idea that when the sun exploded one of those times in its early formation, it sent out a bunch of gases, helium and hydrogen, way out there. And that's mostly what the gas giants are. Those gases went out much further. The heavier stuff didn't get thrown as far, the terrestrial, the irons and stuff. Now, sure, they have an iron silicate core just like we do. In fact, much bigger than ours, but it's mostly hydrogen and helium. How much hydrogen and helium do we have in our atmosphere? Relatively little, yeah. Now, we have a lot of hydrogen that's connected with other things. Water, all your acids, all your bases, lots of things, all your organic matter, lots of hydrogen. So we do have a lot of hydrogen, but it's all caught up in something. Here, it's mostly elemental hydrogen. Now, helium, there's some helium, yeah, but there's not a lot on Earth. Lots of it there. Iron silicate core, just like we have an iron core, they have an iron silicate core. Okay? Jupiter and the other gas giants. So here's sort of the picture, and we'll see a picture similar to this of Earth later in the next chapter. We saw a picture kind of like this of the sun, but it was mostly gases. It wasn't any solid core, because this is a planet. It's not a sun by any means. So we're close. This iron silicate core, just the core inside there, still 10 to 15 times our Earth mass. Our whole Earth, not just our core, our whole Earth. So it's a big planet, a huge planet. Okay, then what you have outside that core is liquid metallic hydrogen. Yo, what in the world is that? Liquid metallic hydrogen. Now, when I think liquid and I think metals, I think that's got to be awfully hot, okay? And I think that must be what's making it there. But then hydrogen, to be liquid, you would think that would have to be awfully cold. So I'm not sure exactly what I mean by that, except that it's a strange combination of things. And look how big that part is. It's enormous, 35,000 kilometers. I don't remember what the Earth's diameter or radius is. Earth radius is 6,000 kilometers. No, I'm sorry. Think of this a minute. Yeah. Yeah, about 6,000 kilometers. Okay, our whole radius is 6,000 kilometers. They are 36,000 kilometers, just in between the core and the next area. That's huge. Okay. Okay. Then the next band here is mostly liquid hydrogen. Okay. Now I know what that means. That's cold. That's awfully cold. In fact, you're talking just a few degrees above absolute zero. I'm thinking 4 to 7 degrees above absolute zero. It's awfully cold. Okay. Okay. And that's a pretty thick layer too. 20,000 kilometers, whereas the whole Earth's radius is 6,000 kilometers. That's huge, okay? That's the liquid. And then the atmosphere is mostly hydrogen, helium, that's like they say there, and ammonia clouds. Anyone know what ammonia is? It's a compound of nitrogen and hydrogen. So it does have nitrogen there, but not elemental nitrogen like we have. It's ammonia, which I usually think of that as being part of amino acids, which are make up proteins. Makes you wonder, but I don't think there's any life ever been there. Not as we know it anyway, but that's their atmosphere. So there's not, when you look at Jupiter, yes.
So I keep wondering about the liquid metallic hydrogen, because the way you explained it, now I thought that I knew what I knew what it was, but now I'm wondering. So do you think that they were saying that it's actual hydrogen metal that's been heated to a liquid and it's spinning?
It certainly is spinning, for sure. We know that. When we say liquid hydrogen, it's so far from the sun, it's really cold. So I think that's why it is. But, of course, there's also pressure involved. There's two things that will make a gas go to a liquid. One is temperature, the other is pressure. And this doesn't act like it's much, but this atmosphere here, if you think how big it is, that still is going to contribute a lot of pressure. So between the cold temperature and the pressure, that's probably what's made it liquid. So it's probably not just temperature. Then down here you have liquid metallic hydrogen, which is hydrogen combined with metals, which would have been solid, but now they're getting so close to that. The pressure is so great, it keeps it in liquid form. That's the best way I can describe it. I may be way off. Okay. That's MBG, my best guess, and that's all. Okay. Okay. An enormous, enormous planet. Okay. Here is, woo. I've been missing some things. This book has a lot of real interesting little blurbs. I've mentioned them before. On page 386 or somewhere thereabouts, there's a case study. Worth the cost is the question. Is it worth the cost? And I think they're talking about space travel, space probes, space sending things up, getting information. Is it worth it? Read this and see what you think. But just the products that have come out of our space exploration make our lives a lot easier. Anyone heard of Velcro? I think that came out of NASA research trying to find something to make things stick to the walls so they don't fly around and butt people in the head when they're in space travel, okay? I think that's why Velcro was developed, okay? I'm not sure on that, but I think it is. So I think yes. I mean, just for the products, not just for that, for the knowledge. How are we going to know it unless we go there and measure it and find out about it? So I'll let you read that. Worth a read. Now we're over here on page 388. They have an example there talking about peak solar energy, blah, 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 blah. We haven't really done the math to be able to do that. If we had done the first half of the book, the physics and chemistry, it'd be easier for us to talk about. We haven't, so I'm not going to do many of those examples. But this picture that you have here is on your page 388 or somewhere thereabout. This is a picture of, not really close to Jupiter, but much closer than we are now, of Jupiter out there spinning. Okay? And notice what it has. Several belts. Okay? Remember that atmosphere? The atmosphere is striated. You know, it has different colors. And what you can't see, within these colors, there's probably lots of storms going on. And this is the biggest one that we know about. It's called their Great Red Spot. Okay? The Great Red Spot. And that's near the South Pole. Okay? Now, they blow up part of this picture right here and show this white spot that's near the red spot. Okay? And that's underneath this. And this says, this is from a distance, this picture, taken from a distance of about 36 million kilometers. That's 22 million miles away. 22 million miles away. The distance from Earth to Sun is 93 million. So you're about a quarter of the way from Earth to Sun as this was to Jupiter when it took this picture. Jupiter is one big baby, okay? It's huge. This great red spot here, I think, could contain the Earth in it. I'm not sure, but it seems like I've read that somewhere or heard it somewhere. It's huge, okay? That great red spot soars about 25 kilometers, 15 miles above the surrounding clouds. It's the coldest place on the planet. Now, it's near its South Pole, that's down here somewhere, but it's still very cold. It's a huge storm. One storm that's been going on as long as we've been able to see Jupiter. So we're talking decades, that one storm. It does seem to be decreasing a little bit. So maybe that storm is fading out some, but it's one big storm. Okay. So what the idea is here, there's storms all over this. This is not just a blob of gas out there. It's got a very active atmosphere. Okay.
Do you think it's because the hydrogen and helium flashes?
Yeah, changes of temperature, yeah. Same thing that causes storms here, hot, cold, you know, and high pressure, low pressure, yeah.
So would they be like the same kind of storms we see, or are they something?
Yeah, only much bigger and much longer lasting, okay. Yeah, it's I'm sure a thermal thing. If that's the coldest spot on the planet, then there's hot air around it, cold air in the middle of it, and and the spinning of the planet sets up a rotation, and it's like one huge cyclone, except that most of our hurricanes are warmer in the middle and colder on the outside, but this is colder in the middle.
Does it have like rain of some sort? No.
It could have liquid, hydrogen, helium, methane, or ammonia or something falling out of it. Yeah, it could be, in a sense, raining on the surface. And I guess with it being so cold, yeah, it probably is. But it's not liquid water.
Okay,
It is some other gas that's becoming a liquid.
Okay.
Yeah, but something could be precipitating. That creates the thermals and the motion, and it's been going on for a long, long time. And by the way, we aren't really talking too much about this, but it's pretty important in the sense of astronomy. The first telescope was developed by, I think, a Danish or Dutch or some Dutch maybe scientist, you know, Netherlands or somewhere in Northern Europe. A guy named Galileo down in Italy read about it, heard about it. He said, that sounds pretty interesting. So he started playing around with the concept. He improved it like 10 times. And he made the most impressive, accurate, you know, easy to manage telescope up to that. Way better than the first one that was done. That usually happens. And one of the first things he looked at early on when he was using that telescope to study, he looked at Jupiter. And what he saw when he saw Jupiter, it wasn't a star, it was a blob. It had a shape. And he saw that shape was spinning. And he said, hey, wait a minute. If the sun spins, and they could tell by sunspots here, if Jupiter is spinning, and Jupiter is that novel thought here, maybe Earth isn't the center of the universe. Now, he wasn't the first to think this. Copernicus was. He had read Copernicus too, and he probably thought, this guy, is there any reason for this? When he saw this, he said, yes, there is reason for that. If Jupiter is spinning, we could be spinning. If we're spinning, then the Earth, the sun may be still, the stars may be still. That path we see them take is not them moving, it's us spinning underneath them. So he began the formula. And it's probably he saw the great red spot. He could tell that was moving from one day to the next. You know, he couldn't take pictures, they didn't have photographers then, but he could tell that it was spinning. Now something else he discovered when he was looking at Jupiter was yuck. Okay. I thought it was going to come here. It must be going to come later. I think I've already hit this. It's a dynamic atmosphere. It's moving. It's changing. As we said before, mostly hydrogen, helium, ammonia, now adding some methane and some water. There is water on Jupiter. And the great red spot, because it's the coldest thing on the surface of the Jupiter, could have some ice falling in it. I wouldn't think it would be liquid water, but it could be solid methane and ammonia too, probably liquid hydrogen and helium. But it has a large system, and I'm not sure the book even makes a guess on it. Let me see if it does. Okay, the great red spot, I just noticed, it has lasted for at least 300 years that we've been seeing it, okay? It is one long storm, okay?
So
I don't know if it knocked the power out or not. No, I'm just kidding, okay? It has many satellites. That's all it says. The last time I saw a number, I think they were in the 50s, maybe more, okay? Has an awful lot of moons, satellites around it.
Seems like Jupiter's compensating for something.
What's that?
Seems like Jupiter's compensating for something.
Yes. And in fact, they think some of those moons may have been ripped off the asteroid belt because Jupiter is so massive, it has such a strong gravitational field that it may have pulled in some what were asteroids and made them moons. Okay. It's a pretty active thing. Okay. Large system. How many, I'm not sure. In fact, that's probably why they don't give a number. There's that same one we saw earlier, great red spot and the white spot near it. And you can just tell by this. Look at that atmosphere. It is a mess. I mean, there's lots of things happening. Very, very dynamic. Okay?
It looks like someone painted all.
What's that?
Kind of looks like someone painted all.
The paint this?
No, I mean, the different colors it has and the clouds, it looks like the whole planet.
Yeah. Actually, I think they took pictures of it using different types of camera, but they made the different wavelengths into different colors.
Okay. So
Yeah, so I think they did this.
it doesn't actually look like that.
Yeah.
They just made
It may or may not, I don't know. But they do call it great red spot, so obviously it is red. And it's probably pretty close, so I don't think it's painted. This may be actually a photograph, just blown up big time. Big, big time. Remember, taken from 22 million miles away, you know, but with color, you know, Kodak film. No, I'm just kidding. Okay. Here we go. These are the 4 biggest moons of Jupiter. And with his improved telescope, Galileo was the first one to see these 4 moons. Therefore, they have a name, the group of them. They're called the Galilean moons. Doesn't have anything to do with the Sea of Galilee or anything in Israel, okay? That's named after Galileo. They're called the Galilean moons, okay? 4 Galilean moons, and these are taken by Voyager 1. Remember, we saw that, I think, around Jupiter. No, we didn't. I mean, Venus, not Venus. Oh, we had seen it. I guess not. There's a lot to start with V, but not Voyager. But it was Voyager 1, took these pictures, and I got to get them right. From clockwise upper left, it's Io, Europa, Ganymede, and Callisto. Okay? The 4 largest moons of Jupiter. And they got more that are even way more out there. Now I'm thinking right now, all 4 of these, the 2 smaller ones are a little bit larger than our moon, the 2 larger ones quite a bit larger. Okay? No, I'm sorry. Io and Europa are about the size of our moon. Ganymede and Callisto are larger than Mercury. Jupiter has 2 moons larger than Mercury. These 2 are about the same size as our moon. Now that leads me to another issue here. Let's think back on our planets, okay? Mercury, how many moons?
None.
Jupiter, how many moons? Venus, how many moons? None. Mars, I'm trying to remember if it has any. I don't think so.
It's got
Or 1 or 2. I think it may have 2. And that may be a couple of asteroids that fell out of orbit and started going around. Why do we have as large a moon as almost as large as Jupiter, which is 318 times more massive than us? Why is our moon almost the same size as those 2 and just a little bit smaller than us? Our moon is really unusual for our planet. It's bizarrely big. Most moons are nowhere close relative size to that. So that leads me also to wonder if maybe our moon broke away from the Earth. There's another feature we'll talk about in the next chapter 2 that leads to that too. Hang on to the thought. Okay. So that's Jupiter. I think that's the last slide we have for Jupiter. Now we're moving on to Saturn. What do y'all know about Saturn?
It's one of the rings.
The rings. Now actually all the gas giants have rings, but Saturns are outstanding. You can see them from the Earth. They're just absolutely beautiful. Okay, let's go back to our sun. Okay, here's the sun here, remember? 4/10 of an astronomical, here's the sun, look at that. Okay, 4/10 of an astronomical unit, we have Mercury. Then 7/10 we have Venus. 1 astronomical unit, that's us. 1.5 we've got Mars. 5, I think we're somewhere out in the hall now, we've got Jupiter. Almost 10 before we get, so we've doubled the
We're
distance.
probably now from over there.
Yeah, we're over some other walls over there. Way over there, okay? So that's why I said that figure back on page 381, they don't have the distance anywhere close. Nowhere close, okay? Nor the relative sizes. Okay. Now, rings of particles, beautiful rings of particles. Here's just one pictorial. This is from, I think, Cassini-Huygens. I'm not sure, but someone took this picture. It's just incredibly pretty. They're pretty from the Earth, but up close they're even amazing. Okay, now here is this, to me, the strangest thing. Yeah, the rings are there, beautiful. That's what sets Saturn off. But here is, to me, the strangest thing about Saturn. Even with a dense iron core, everything else, the whole planet, on average, would float on water. 7/10 the density of water. If you had a tub big enough, which of course no one does, it could float the whole planet. Okay, you're okay. I want to make sure you pay attention before I let you in. Okay. All right. So this is Saturn. The rings are obvious. The amazing thing about it to me is its density is so low. Okay? Now, its surface, very similar to Jupiter. And what kind of surface is that? Gases, liquid hydrogen and helium, and then somewhere down there you get liquid metallic, somewhere way in the core before you ever have a solid surface, but that's way below, way below the surface. Now, remember we said, don't know exactly how many satellites Jupiter has. I think it's in the 50s. Saturn has around 30 satellites. Titan is its largest one. Remember the Titans, right? No, okay. Titan is the largest of its moons, and it's the only moon in our solar system with a substantial atmosphere. Okay. Most of the time, you don't think of moons having atmospheres. Titan, I think, maybe actually larger than Ganymede or Callisto, the largest moons of Jupiter. It's a huge moon, and it's the only one in our atmosphere in our solar system with a substantial atmosphere. So,
That's so possible.
what's that?
That's so possible.
That's
That?
how is it possible? Well, if you think about it, all the gas giants out there are surrounded by gases, but it happens to be Titan is big enough, it attracts some of the gases around it. It's not an atmosphere like ours. It's probably hydrogen, helium, methane, ammonia, maybe a little bit of water vapor, but that's.
So wouldn't it have to be magnetic too then?
Well, it doesn't have to have a magnetic field, it has to have a gravitational field. And being that massive, it's going to have a lot of gravity. So, my guess, it must be more terrestrial. I don't know this for a fact, but it must be fairly dense as well as being big so that it does have enough gravitational attraction to pull in an atmosphere. And if you think about it, Saturn has a lot of things around it that it could have that. Yeah.
So in space, all the gases basically group together, right? To form something. They don't just. So what is left in space? Nothing, or is there actually like traces of gases?
Oh yeah, there's traces like. Let's take the ball on the ballpoint of a pen. Okay, if you were to take that small little ball of gas from this room, it probably has, I'm guessing, trillions of atoms or molecules in it. I mean, they're very tiny, but they're very far apart. No, yeah, but there's still a lot there. If you go to outer space and take something, say, the size of a basketball, you just have a few, maybe tens or something. So far less dense than our atmosphere, way less dense, but there are particles there in space, just knocking around, hardly ever bumping into another particle. Very lonely out there. Okay. Right. But yeah, there are particles in space. It's just very far apart. So basically the pressure is acting like zero.
Oh, that's okay.
Yeah.
You've explained.
Yeah, because there's so few that there's not much weight to them at all. So far apart. Okay. You get all this? Okay. Let's move to the last two of our planets. Remember, Pluto's no longer a planet, a dwarf planet. The last two are Uranus. Okay. Wait, let's start over again. Sun, you're still there? Okay. 4/10 of an astronomical unit.
That's
Mercury. 7/10 of an astronomical unit. Venus. 1 astronomical unit. Earth, us. 1.5 astronomical units. Mars. How far to Jupiter? 5. How far to
Right there.
Saturn?
10.
Almost 10, 9.5.
Go across the-
You almost double that again. 9.5 times 2 is 19. So the whole distance from the Earth to Saturn, that much further before you hit Uranus. Okay? And please put the accent on the first syllable. Number one. Okay. Now, all right. After that, Neptune, not quite twice as far then, way, way, way out there. In fact, we didn't even know about Neptune till fairly recent. Okay, Uranus even, it's not been that long that we've known about it either. These are the outermost gas giants that we know about. When they wrote this book, they acted like they were the last two out there. Yes.
That's all we know from other new planets.
Okay, that's exactly what I was getting at. Just in the last year or so, though I'm sure they've been collecting the data for a lot longer, they are collecting enough information to suggest that there might be yet another one out there. Another pretty good sized one, okay? Probably on the order of these, or maybe even, I don't know if it's big as Jupiter or not, but there's gravitational data, there are other things out there, but it's so far away, we hardly see any reflection off the sun at all. But there's enough data. In fact, that would be a fantastic paper topic. In fact, you might be able to write on 2 or 3 different things about it that contribute to the theory that there's yet another planet out there. Not another dwarf planet like Pluto. Pluto's a little rocky thing that's smaller than Mercury. We're talking about a real size planet out there that we think may still be there. Okay? Maybe worth a paper topic. I mean, that would be a fantastic one. But these are also your gas giants. Okay? Looking at each other, it's almost like they're twins. Okay? That, I think, is Uranus. Let me check and see. The pictures look so similar. Oh, in your book, by the way, I meant to mention this. They have some more figures that are not shown on your slide set, so read your book. One of these, and I mean, this is sort of jumping over the place, but there was a comet, Schumacher-Levy 9, okay? Comets go real close to the sun and then way out there. We'll talk about those later in this chapter. Way out till you come back in. Schumacher-Levy 9, I think this was around 1994, made a bad mistake. Too close to Jupiter. Jupiter basically pulled the comet apart. There is no Schumacher-Levy 9 comet anymore, and the picture you see on page 390 or thereabouts in your book. Now, what famous astronomer got this picture of these spots going across Jupiter's atmosphere? There wasn't one. An amateur astronomer who just liked looking out into space using his telescope said, what are those spots on Jupiter? I've never seen those before. He called in the thing and said, hey, I see some spots on Jupiter. He said, where? And look up. Oh, there are some spots. Where'd they come from? That was what was left of Schumacher-Levy 9. It got too close to Jupiter, and it broke it into at least 22 pieces that they can tell, lined in a row, plummeted into Jupiter because of Jupiter's enormous magnetic field. And this picture here was made by the Hubble Space Telescope, but he saw it first, just with his little telescope. Okay, so it doesn't hurt to look at the stars. Okay. Now, I was trying to find this one. This is Neptune. Sorry, this is Neptune. But guess what? It's hard to tell them apart.
Uranus was sideways.
Yeah, Uranus is the one that spins backward, but also its orbit is not upright, even at an angle. It's almost horizontal. So it's spinning like this. I don't know what morning and evening look like there. I mean, the sun does some really weird things on that, planet to spin like that. So, and backwards at the same time. So yeah, that's two things to note about Jupiter. I mean, Uranus, and you get those from that table that's early in the chapter on page 382 or thereabouts. With Uranus, it says its rotational period is negative 17 hours, whereas ours is positive 24 hours, theirs is negative 17. Compared to Venus, the other one that spins backwards, negative 243 days for it to spin one time. So it's going backwards, but very, very slowly. Uranus going backwards, but
The spin is the opposite.
yeah, spinning the opposite, and then also at an angle that's almost horizontal. So it's spinning like this. It's how could that happen? Very good question. Now, one of my ideas, and this is just my wild, I don't know if y'all know what a wag is, but we won't go into that. But one of my wild guesses would be that I wonder if something collided with the two of them and they split apart and one spin one way, one the other, because they're almost the same size if you look at them. The spin on Uranus, minus 17 hours, on Neptune, positive 16 hours.
So you think there might have been one planet originally?
I'm just guessing, way wild guess, okay? But yeah, I wonder. But they're so far apart. I mean, it's as far apart from Uranus and Neptune as it is from Sun to Uranus, just about. I mean, not quite, but they're still.
Well, it is kind
it's
of
just
strange.
amazing.
They are the same size.
How's that? Yeah, they're almost the same size, and they're just about identical in structure, similar internal structures, just for everything. So,
Yeah, because it seems they keep getting bigger until we get to those two.
what's that again?
Seems to get bigger until we get to those two.
Yeah, well, Jupiter's the biggest, and then Saturn's smaller, but still bigger than these two, but yeah. And if that next one out there that Carl was talking about is even bigger, then that would lend more thing that maybe it helped pull them for. I don't know. It's interesting. That's what's interesting about astronomy. You can just have so much speculation here. And of course you have to do the math to figure out if any of this is possible. Okay. I think they're probably going to show a slide here on the inner structure. Whoops. All right, here's the one I was talking about. They got these slides. Oh, no, I'm sorry. They're going to the next one. That's why it was late here. In the book, on figure 1514, is a picture of the structure of Uranus and Neptune. They're almost identical. They have a rocky silica core, just like Jupiter did, but then they have this in between. And they say it's mostly water and water ice, as opposed to liquid metallic hydrogen and liquid hydrogen. It's water and water ice, which is really interesting because it looks like most of the planet, these two planets, back a slide, have a significant amount of water. But it's ice water. It's life. No, too cold. Nothing else fits for it. They say about 8,000 kilometers, which would be about 6,000 miles, which would be almost the radius of the Earth, would be outside their core before you get to the surface, would be water and water ice. That's amazing. There would be that much there. So if we ever run out of water, just run out to Neptune or Uranus and pick up some. A tank full. Okay. Okay. Yeah. Dreaming. Okay. Now I think we're ready to go. The figures and the pictures are on the pages are just sort of wacko here. The next slide takes us into the next feature here, which is the smaller bodies of the solar system. Someone name what some of these are.
Asteroids.
Yes, here we have it right here. Comets, asteroids, meteorites. Now, I really don't like that naming. If they're going to say this, they should say comets, asteroids, and meteoroids, not meteorites. Meteorites are the things that land on the surface of the earth. It should be meteoroids in my mind. Okay? Now, remember we talked about star formation. There was a lot of really messy stuff going on when those initial fusion reactions blew the star apart, and then the gravity pulled it back together, and then it sort of reached that dynamical equilibrium. There was a lot of messy stuff going on. Some of that messy stuff is the leftover from the solar and planetary formation. When it did blow things up, it left stuff floating around out there. Planets were the bigger chunks. Their moons would be the chunks of that, the asteroids, but then the rest of it, the comets, the other meteoroids and stuff, that was just leftover junk that didn't really fit into any place very well. Let me put it that way. Now, this statement cannot be true if you believe the first statement that we read early in the chapter, and I tried to make a special effort at reading it to you. The mass of the smaller bodies may be 2/3 of the total solar system mass. Okay? That's a statement. It's in your book. Let me read you early in the chapter. Okay? Got to find it again. I thought I had it right here in my eyesight, and now I've lost it. Okay? Here it is. On page 380 or thereabouts, second column, second full paragraph under that. The sun has 700 times the mass of all the planets, moons, and minor members of the solar system added together. Okay? So what do they mean by that statement there? Except for the sun. When they say solar system mass, they talk about everything except the sun.
So they're talking about like rocks, gases.
Yeah, the planets, the moons, the asteroids, everything else except the sun. Because the sun has 700 times the mass of everything else put together. So obviously this couldn't be 2/3 of the total solar system mass. That's 2/3 of the total solar system mass outside the sun. Okay, that's what it means. But it's still pretty incredible. Jupiter, 380 times as big as the Earth. And then all these other planets, Saturn and Uranus and Neptune, all many times bigger than the Earth. In fact, the core of those others are about the same size as the Earth, okay? So that's a lot of mass. And then all the moons. But then, if you count all these other things, they are tiny. Comets, asteroids, meteoroids, that should be it, meteoroids. They are 2/3 of the total mass outside. So all the planets and their moons is 1/3, and everything else is 2/3. So there's a lot of these things out there, a whole lot. They're just really small themselves, but there's a whole lot of them. Now these things also come in because the sun pulls them in, and they bombard the other things, the larger objects. And here it is, Comet Schumacher-Levy. And let's see if I can, never am quite sure where they're talking about here. I think it must be here, but that doesn't look anything like this. But anyway, somewhere here, this is Jupiter again, okay? And the fragments of Comet Schumacher-Levy are those 22 pieces you see scattered there on the surface of Jupiter, okay? They struck Jupiter in July 1994, first detected by an amateur astronomer who just happened to be out there looking at Jupiter one night and said, I don't ever remember seeing those. He must have been within just a few days or something of when it actually happened. He got the professional astronomers to look at it, and then they took this picture with Hubble Space Telescope. Okay, I wanted to point out that's not The total solar system with the sun is the total solar system outside the sun. Otherwise, the two statements can't be true. Okay. Now, second, you got it. Okay. Now, let's start with comets. There are two major regions in which there are comets. The outermost of these is called the Oort cloud. Now, that must be named after somebody, and I'm guessing maybe some from Netherlands or maybe Baltic area, somewhere up there. That's such an unusual name. But anyway, the Oort cloud. It'd be a good paper topic if anyone wants to choose who in the world was Oort and what did he study on this. There's several topics you could do. The origin of the long period comets, and when we say long period, those whose period around the sun, all comets go around the sun, about 200, greater than 200 years. These are from way, way, way out there. And these are from 30 astronomical units. Now remember, what was the last one we got to? We had Jupiter at 5, Saturn at 9.5, Uranus at 19, and Neptune way out there around 30, wasn't it? Okay, around 30. Okay, so these are comets who are way out there beyond Neptune and up to a light year away, a full light year away. One astronomical unit is 93 million miles. A light year, goodness gracious, I don't even remember how many millions that is. Let's see if I can find it. Oh, I don't think it would. Light year, it's about 9.5 times 10 to the 15th meters. Lots of zeros after that one. Way more. So this is way, way out there. I wasn't even sure our sun had effects out to 1 light year away, but obviously it does. Okay? So that's the Oort cloud, way out there. Now inside that, and I've heard this pronounced a couple of different ways. I think it's called the Kuiper belt, but I've heard it called the Kuiper belt, okay? Depending on what country I think it is. Okay, let's call it Kuiper. It's a little easier to pronounce. The Kuiper belt. Who in the world was Kuiper? Okay, there's another paper topic. The origin of the short period comets, those are less than 200 years, and it's a disc-shaped region that also starts at 30 astronomical units, but only goes to about 100 astronomical units. Now, here's the two differences here, if you notice. This is a cloud. This is a belt. A belt is a disc-shaped region, whereas the cloud is the whole three-dimensional region. Okay? They both start at 30 astronomical units, or thereabout, but this one goes to a light year away. This only goes to 100 astronomical units. 100 times as far as we are from the sun. That would be 9 billion, 9.3 billion miles from the sun. Wow. Okay. Now let's see if we can get a picture of them. Yeah. Okay. Now, just to get an idea here. Okay. Here's our sun. Here is the orbit of Uranus. There's the orbit of Neptune. This is the orbit of Pluto. See how out of line that is? That's why it's a dwarf planet. It doesn't fit. All the other planets are in the same disk here, okay? Just closer and closer to the sun. But Pluto's way out of line. It's far more elliptical. It's far more terrestrial, and all these out here are gas giants. It just doesn't fit. That's why it's a dwarf planet, okay? But this whole part of our solar system here, and this is, I can't read that off the slide. about 10 astronomical units. No, that's not 10. What's that, 50? 50 astronomical units. Okay? That distance across there, remember, Neptune was 30, so that would be 60. So yeah, that's about right. Okay, so that's 50 astronomical units. Okay, this whole thing then would be, it's 50, 100, 150, maybe 200. 200 astronomical units fit right in there. That little bit right there. That tiny little bit right there, okay? That's everything we know. All the planets, okay, including Pluto, is right there. Look at this. There's the Oort cloud, okay? There's the Kuiper belt, okay? Way beyond our solar system. This is why 2/3 of the mass of the solar system, except for the sun, is in this. It's so huge, and there's so many bodies out there. Can't even, no one's even come close to counting them all. That's why they have 2/3 of the mass of the solar system, not counting the sun. Okay, so what happens? Well, I like this term here. It doesn't sound very scientific. Gravitational nudges. You know, gravity just sort of pulls it a little bit, nudges it, and it deflects it, and here they come in toward the sun. And they come in and get relatively close to the sun, speed up as they do, and then go flying back out there again. Okay? This is the comets. There's a lot of them. Two areas, the three-dimensional Oort cloud and the disc-shaped Kuiper belt. Okay. Now, I wish my computer was over here. Okay. What do comets' structure look like? Okay. Well, they're small. Okay. They're mostly solid. Small, solid objects. Some people have called them dirty snowballs. Okay. Because they seem largely to be made up of ice. But ice with chunks of rock embedded in it. Dirty snowballs. Don't throw them at one another. They can hurt. Okay. And this is one model. Frozen water. What's CO2? Carbon dioxide, but guess what? That's frozen too. We call it dry ice. Okay. These are cold things. Okay. Ammonia, which is probably also frozen. That's NH3, ammonia. Methane, anyone know what methane is? CH4, another compound, probably also frozen. And in the midst of all those frozen things that are normally liquids or gases, we have dusty and rocky pieces. Therefore, they're dirty snowballs. Okay. Now, when you see them, what you'll see is the head, the comet head. That's a solid nucleus, and around that is a coma of gas. Okay? Because carbon dioxide, ammonia, and methane are generally gases. They're solid in the core, in that nucleus, the head, but especially when they get closer to the sun, they begin warming, and the gases are vaporized from the solid, actually sublimated, going straight from the solid probably to the gaseous state. You're at such low pressures that they probably just go straight to gas, no liquid. Okay, so you're surrounded by this coma of gas. Now, there's two types of tails. You have the head and the tail. Now, it's not like a coin. It's quite different from that. And in fact, I hope we got a figure here. Here we have. Here is the head, the nucleus, somewhere down in there, surrounded by a coma of gases, and then you have the streaming gases or things coming out. So the two types of tails. One is ionized gases. What do we mean with the term ion? Ionize.
The atoms are missing.
Not atoms, electrons.
Yeah.
Either electrons are extra or deficit. Okay? See, a neutral atom has the same number of protons in the nucleus as it has electrons in the cloud around it. Okay? That's a neutral atom. To be an ion, you have to have an unequal, either excess electrons or deficit of electrons. That makes it charged. Because it's charged, it can give off light. Okay? So ionized gases can give off light. Are there any ionized gases in the room right now? Yeah, in the fluorescent tubes. There are ionized gases in that. Now, in a light bulb, that's not ionized gas. That's just heated filament or something like that that's giving off light. But in those fluorescent tubes, we have ionized gases. They're flying down, up and down the tubes, going between two charged, the ends. The ballast creates a different charge at each end, and it pulls the ions both directions. You know, if they have an excess of electrons, they're negatively charged. If they have a deficit of electrons, they're positively charged, so they're going opposite ways. Those flying past if you've ever broken a tube, don't do it on purpose. If you ever have seen one, you know that white powder that's inside the tube? That is a phosphorescent material that when these ions go past, it excites an electron and it jumps up a level. You know, electrons live in shells. It jumps up a shell, and then when it passes, the electron doesn't have any reason to stay there. It falls back down, and that distance it falls is related to the wavelength of the light that's given off, and that's why it gives off light. It's a material that gives off white light. Okay? So the ionized gases can be giving off light, but also dust. Now, dust doesn't normally give off light, but dust reflects light. And when do we see the comets? Out there in the Oort cloud? Nah, you aren't going to see them out there. You can't see that far. When do we see comets? When they're close inside the inner part of our solar system, coming down. Now they're close enough that dust is going to reflect sunlight. So the ionized gases here and the dust that's also here reflecting sunlight, and that's why this is glowing, because ionized gases are reflecting light from the sun. Now, where is the sun in this picture? You don't see it, but where would it be? That way, because the head, the nucleus, head or nucleus is always pointed toward the sun. When it's coming in, it's pointing to the sun. And when it leaves, the head is pointing to the sun. The tail is going first. It's not a projectile, okay? The head always points toward the sun, even when it's on its way out. The tail is back here. The head is still, you're the sun, right? Okay, always pointing toward the sun. On its way in and on its way out, the head points toward the sun. Okay. The tail points away from the sun. Oh, okay, got it. Okay, tail always points away. So whichever way this is on its way out or on its way in, the sun's that way. Exactly that way. All right, any questions? Let's do more on, whoa. They skipped a whole lot on the comet structure there. Let me hit a couple more things for you. No, sorry. I was thinking meteoroids. We're fine. That's all on comets. Next was asteroids. Now, comets live way out there, and occasionally from gravitational nudges come toward the sun and then go way back out there and stay out there for a while. Asteroids, though, generally stay between what two planets? Mars and Jupiter. Very good. Oh, right there. Y'all are good, aren't you? Okay. Located in a belt between Mars and Jupiter. Yeah, Terry just picked up on that. Never mind. Okay. All right. Now, there are a variety of sizes, up to about 1,000 kilometers across. Now, how does that compare to the Earth? How big is the Earth? The Earth's radius, on average, about 6 million meters, which would be 6,000 kilometers, which would be about 4,000 miles. Okay, but 6,000 kilometers. This is 1,000. So a good bit smaller than the Earth. In fact, a good bit smaller than our moon. Okay, so they are nowhere close. But remember, we have a big moon. They have varied composition. The inner belt, remember you have Mars, asteroid belt, Jupiter. The inner part, those that are closest to Mars, remember what the 4 inner planets are called? Terrestrial planets, we mean they're rocky. And these will be your stony asteroids that are closest to the rocky planets. Okay? The outer belt are dark with carbon. Now, I don't know exactly what that means, okay? I really don't. Dark with carbon. That must mean, rather than just being stony here, they have carbon buildup on the outside. Now, I can't even imagine why that's the case, but that's what it says. In between the inner and outer belts, they're mostly iron and nickel, which to me is sort of sounds like it's stony. But this means specifically iron and nickel. Now, we've mentioned iron and nickel before. Where do we mention that? The what? Yeah, the core of the Earth and many of the other planets, that's what it's mostly made up of. So this is basically, you have the stony, would probably be stuff like on the surface of the Earth, our silicates and stuff. Yeah.
So the asteroid belt should have been another planet?
It sure seems like it should have been, with the core being the inner part, and then the stony, and then maybe carbonaceous. Yeah, it makes you think that. Formed from the original solar nebula. Okay, remember, you had a cloud of gases. They started, something nudged them toward the middle. They started attracting each other, gravitational attraction, build up mass, build up pressure, build up temperature and stuff until it drew in so much, got so hot, fusion started happening. When fusion happened, it blew up, but then it pulled back and it developed this dynamic equilibrium. That was the original solar nebula, okay? That's when this started. They think it was prevented by clumping into another planet because Jupiter was just too big, too much of a bully, okay? Wouldn't let it form, kept it separated, and so we have a cloud of asteroids. And if you, and we'll do this later in the chapter, if you look at that, you would think there would be another planet between Mars and Jupiter. It seems like it would fit. The distances, it seems like it would fit, okay? Everything seems like it was. Jupiter's the culprit. It was a bully. It kept them from forming. Kept it from forming. So here's how you would talk about it. Remember, Mars is about 1.5 astronomical units from the sun. Okay? So let's start with Jupiter, though. Let's say a Jupiter unit. This is here. 4/10 of this is where the asteroid belt begins. 6/10 is where it ends. It looks like that should have been another planet somewhere in there, but Jupiter's gravitational field was just too strong to keep it from happening, it appears. Okay? The inner part were the stony part, the outer part, dark with carbon, whatever that means, in between iron and nickel.
So what's making the entire belt stay within that vicinity? Is it
Good question. What we'll do a little bit later in the chapter, in fact, it's the next section, talk about how the solar system was formed. And after the explosion, then the groups of matter sort of got together and became the planets with their moons and stuff. Sorry. And they clumped, but couldn't clump into a single planet. Jupiter kept that from happening. So it's sort of the location that it would have been, but it just never could get together, probably because of Jupiter is what they think. But that's where the clumping would have been. And that regular pattern that you get of almost doubling every time, that would be the centers of the mass there. I think, I'm not absolutely certain of this, but I believe there's a mathematical model. I'm trying to think who it's named after. It may be Laplace, but that doesn't seem right. But one of those mathematicians, maybe Legendre, I can't remember which one, has a model in that it almost predicts this is where the groupings would have been. But Jupiter, and there's also something, again, I'm sort of fuzzy on this, but the biggest gravitational field is right there, the sun. The next biggest is here. And it's kind of a interaction between these two that keeps, this makes it sort of no man's land.
And see, that's what I was thinking, but since Jupiter is just in that one spot, the gravity, like their gravitational pull will only affect what it's next to right then. Right. But on the other side, the sun is still, pulling it in. That's why I kept thinking.
Yeah, I think the sun gets involved with it there somewhatly too, and it's they're called nodes, and they tend to have smaller groupings, but not enough to make a single planet. Yeah, I think it's really fuzzy back there in the nether spaces. Okay. All right. Now let's get to the third group of small objects. Comets way out there. Two belts. What are there? Two groupings. Comets. How long ago? Say again?
You said the meteor.
Okay, yeah, we're going to get to these in a minute. This is what we're getting. This is review now. Comets.
Asteroids.
Okay, asteroids and meteor. Actually, I think it should be meteoroids. But let's go back. Let's review comets. They were in two groupings. The what? Kuiper, the Kuiper belt. Those are the closer ones, and the Oort cloud, which are the way, way out ones. Okay, then we have asteroid belt that are basically along where a planet would be. Then the third grouping are, and why they say meteors and meteorites, they really should just say meteoroids. These meteoroids are the remnants of comets that passed by, and remember, they were giving off dust, losing chunks of rock because the ice was melting and pieces of rock. Well, this pieces of remains, the things, those are meteoroids scattered throughout our solar system and beyond. I mean, just out there. Like you say, it's particles that are out there. Okay, now the meteoroids are those pieces that are just out there. When our Earth happens to go in its path around the sun and goes through some of these meteoroids, and they hit our atmosphere and go under the influence of our gravitational field, then they're pulled toward us. That's when they become meteors. They're not meteors when they hit Jupiter or when they hit Mercury or when they hit the moon. They are meteors when they enter the Earth's atmosphere. So the meteoroid encountering the Earth's atmosphere, and then it comes and starts burning up as it goes, and that's what forms the shooting stars of the falling stars. They're not stars. They're pieces of junk, leftover comets or asteroids. Now, you might say, why asteroids? If you picture this, big cloud of chunks of rock out there, as they come close to each other, they may actually collide some, and then one will gain energy and another will lose energy. If it loses energy, it's going to go out of orbit, and it starts falling toward the sun just like a comet does, except it's just falling toward the sun, and if we happen to intercept that, it becomes a meteor. It was an asteroid, but now it's a meteor. It was a chunk of comet, now it's a meteor, okay? Remnants of comets or asteroids, okay? Now, why do we have meteor showers?
big asteroid, you said a small asteroid with a bunch of chunks of rock.
Okay, if that did happen, that would certainly do it, but most of ours are from the comets. The comets come across our solar system and go way back out again, right? They all do this, not all the time, but they're, that's their pattern. And when they come, they're losing mass. They're trailing pieces of dust and rock and things because the gases are getting closer to the sun. They're losing. Then they go out again and they may pick up some more later. I don't know what they do out there. Okay? But this trail of dust, it's there and we go through it. And now we have a meteor shower. When we go through where a comet has been, or perhaps, like you said, an asteroid coming down, maybe disintegrating too, I don't know. It could be there too, but they're mostly where comets came. Now, what makes a meteorite? That meteor enters the Earth's atmosphere, starts burning, that's what we see, that's what makes it a meteor, a falling star, a shooting star. If it burns up completely in our atmosphere, it never becomes a meteorite. But if some of it doesn't burn up completely and actually impacts the surface of the Earth, then it becomes meteorite. Okay, now, yeah.
Aren't meteors kind of dangerous depending on where they hit?
If they hit you, yeah, they're really dangerous. Yeah, you're right. Yes.
Where does the energy come from with the comets? Like, what gives it so much energy to continue to?
It's the gravitational pull of the sun. That's what does it all. Because it's way out there. Remember, gravitational nudge, it got it falling, and as it does, it's coming toward the sun, always coming toward the sun, picking up speed as it comes, then it whips around the sun, it's at its fastest speed, and then goes flying back out there again. So what gives it the energy is the gravitational attraction. Yes.
How much mass does a meteor need to outburn the atmosphere?
I don't know. That's an excellent question. I'm sure there's some calculation on that. If you're that interested, you could write a paper topic on it. I bet you could find the data somewhere there. It really would be interesting to know. And probably a little bit more of what the composition is. If it's what they call the stony, then those are probably made out of the silicates. They would probably burn up faster than the iron ones would. So it probably is part mass, but also part composition. So there's probably a combination of things, but certainly the mass would be, I think, the major one. So that's a good question. I just don't know the answer. I should look it up. I'm saying, why don't you look it up? Okay.
I'm surprised it wasn't in the lesson.
Was that? Yeah, I know. I haven't seen it in the book anywhere. I'm not sure they actually know. They probably have some theories or rather write something that they're not certain about. You just left it out. Or you didn't know either. I don't know. Okay, so that's when the meteoroid that hits our atmosphere becomes a meteor, and it makes it all the way to the surface, then it becomes a meteorite. Okay. Now, remember, it could have been a part of a comet, or it could have been a part of an asteroid. The asteroids, in my mind, are much larger than comets. So my one answer to yours, if it started off being an asteroid, I think it's a lot more likely to ultimately make it to the surface. In fact, not too long ago, I'm thinking within a decade or so, a pretty massive, and I think it was from an asteroid, meteorite did hit the Earth. Fortunately for us, it was somewhere out in Siberia, where the population density is very sparse. But there was a town close enough by, they saw the fireball as it fell. And they probably were thinking, well, the U.S. had pushed the button, but it wasn't us. But they did some study on it, and they pretty sure it was an asteroid, okay, originally, which became, once it was loose, floating around out there, it became a meteoroid. When it hit our atmosphere, it became a meteor, and since it didn't burn up all the way in, it became a meteorite. Okay. Now, it just happens to be that where I grew up in Georgia, our farm, we find chunks of really dark looking rock that rusts, so it has to be iron based, and it's dense, it's heavy, and sometimes it's really smooth and strange looking. It almost looks volcanic, but that's the last volcano we knew about in Georgia. We don't know of any, okay? And what I think it was must have been a meteorite. It must have been pretty big because they've done some topographical studies, and there's sort of a big occurrence covering a lot of area of remains of this thing. And it makes us wonder, I could think of it, I don't think we brought any to Birmingham, but next time I go to Georgia, but it'll be spring break, this class will be over with, I'm sorry. But maybe I'll try to remember to bring that for my subsequent classes. I don't know, everybody that we've asked about has a different opinion, but we'll see. Now, how do we classify these meteorites that do make their way all the way to the surface that we've been able to study? And by the way, if you've got your text on page 395 or thereabout, what I'm describing looks a lot like that, okay? Figure 1519A. Now they call that a stony meteorite. The smooth black surface was melted by compression of the atmosphere, and then the B one says an iron meteorite. But this one's been cut, polished, and etched with acid, so the color is nowhere close to what it should be. I don't think. I would have called A more iron looking, but they say not. The pattern indicates the original material cooled from molten material over millions of years. That suggests that when the sun blew up one of those times, threw stuff way out there into the solar system, that hot material that was blown up there cooled very, very slowly over millions of years. That's what it indicates there. Okay. But let's talk about some of the characteristics. This is on page 395 underneath that picture, that paragraph on the left-hand column, right near the bottom of the page. Meteorites are classified into three basic groups: the iron meteorites, the stony meteorites, and the stony iron meteorite. Boy, what a classification scheme. It's iron, stony, and stony iron. Okay? Now, the stony ones have a further classification. They are either chondrites or achondrites. Well, what do we mean by that? A chondrite has a structure of small spherical lumps of silicate minerals or glass called chondrules. Boy, what weird terminology. Have any of you ever been around some of these blast furnaces where they make iron and seen some of the, they heat iron to the ore to very high temperatures so that the Bible calls it the dross, the contaminating stuff vaporizes and goes up and then cools into little spheres. That to me is what they mean by chondrules, those little spheres. Okay, so if they have the little spheres, they're called chondrites. If they don't have them, they're called achondrites. That would be the stony materials, indicating how that stuff cools. Okay. Nothing replaces reading the chapter. I've said it many times. Please read the chapters. I think this stuff will make more sense to you if you read it. And I think also, as I told you, I read it time after time after time before I ever had the confidence to teach this course, just because I wanted to understand really what was going on. Now, I was supposed to call roll at 3 o'clock, wasn't I? And I forgot to do that, but let me call it now. What's that?
I think there's 3 people that work here.
Yeah. Brendan's still here, so I guess I have to count him here. Brianna, yeah, is still here. Dalen, yeah, is here. I'm still learning names and faces. Darius left, was it?
It was about 15 minutes here.
15? He's generous. Yeah, okay, I'll count him as here. Emmanuel is kind of here, I think. Yeah, he's still here. Tara is still here. Very good. Coco. Yeah, there you are. All right. Okay, Bianca. Got it. Thank you. James. Yeah, he's still here. Josh is still here. Gary's still here. Charles left to already. No, just kidding. Okay. And he's disappearing fast. The guy named Stevens we haven't seen from the beginning. Last name Stevens. Shelby is still here. Yeah. Brittany's still here. I forgot the mark. You still got my Brittany, right? And Terry's still here. Right. Okay, good deal. Guess we didn't lose anyone, supposedly, or 3. All right. Here are some of these meteor showers. Okay? And these are named, my best understanding, from the constellation where you'll see them the best. And by the way, this is on page 394 there by about bottom of the second column. The quadratid is on January 3rd. We missed it. Okay? But I remember them talking about this on the weather that night, about the meteor shower. Wish I'd seen it.
Annual meteor shower?
Yeah, these are annual. Okay, if you think about it, it takes us 1 year to go all the way around the sun. So if this comet came through here, we're going to hit it just about the same time every year.
So there was a comet.
It was the leftovers from comet.
And it's still in the same spot. And
Well, the dust is there. When we go through and, it may move a little bit and we get some of these every time. It left a lot of dust, okay? And you'll see about 30 an hour, that's about 1 every 2 minutes. That was one of the more prolific ones we'll see. Aquaid, must be an Aquarius, May 4th, only 5 an hour. That's one every 12 minutes. I'm not sure I'm going to have the attention span for that one, okay? Perseid, there's a constellation called Perseus. August 12th, that's about 1 every 4 minutes. Okay, 15 an hour. No, I'm sorry, 40. That'd be 2 every 3 minutes, okay? So that's pretty frequent. Every minute and 20 seconds, you'll see one, okay? Orionid, that's in the constellation Orion, one of my favorite constellations. That's only 1 every 4 minutes, around October the 22nd. And Taurid, in Taurus, the bull, I guess the comet came in and went out near, and we must pass through both of those, and we see one on November the 1st and again on November 16th, about 1 every 12 minutes. Leonid and Leo the Lion, that constellation, about 1 every 12 minutes. November 17th. Boy, 16th, 17th, we'll see a few, but they're long times between them. And Geminid in the constellation Gemini, around December 12th, that's the most frequent, almost 1 a minute. So if you can remember to, these bigger ones, try to go out some of those nights and see. They'll usually tell you on the weather station, weather channel, or one of the local weathermen if we are going to have one, or email them and ask. Say, when is the best time to see these? And it may be early evening, midnight, late, they'll usually let you know. So those are some. None coming up between now and the end of the term. Sorry. Okay. Mini term anyway. All right. Those are the 2 pictures I showed in the book. These, believe it or not, are called stony. These are called iron. To me, they look backwards. This iron has been treated as with acid. Huh?
I think the black one would be iron.
I would think so too, but they call it stony. And my guess, this may be, I don't know. It
kind of does look like it's 17.
Yeah. What it also to me looks like volcanic glass, what they call it, something that's cooled really quickly and didn't have really the crystal structure that it would have, and it has a glassy appearance. I wish I had some of those from home. They look sort of like that. They feel heavy like iron. Okay. So now we get to, I think this is the last section in the chapter. No, there's one more after that. Okay, the origin of the solar system. Okay, we've already been talking about it. We talked about it sort of last time. Here we get it big time. All right, if you remember, a star is formed, not born, but formed, when you had this mass of gases and something perturbed it and they started collapsing on themselves. The masses started collapsing. And as they got denser and closer and more friction, they heated up. As they heated up, and got bigger, they drew more mass. You know, the gravitation was sort of a unstable equilibrium. It just kept growing, getting more massive, kept getting hotter and hotter and hotter until it finally reached the point of fusion. We talked about this in the last chapter. Okay? At that stage, fusion begins. Now, it's not gravitational collapse anymore. You got a huge fusion nuclear reaction blowing things outward. But gravity is still pulling them inward, but in a time there, you have a lot of mess going on. That, to me, is when we're talking about the protoplanet. This is beginning of a planet, the nebular model. Okay, nebula meaning it started with the cloud of gases. Okay? First stage, the formation of the heavy elements in many earlier stars and supernova. So in other words, remember, where did this iron come from? Where did the uranium come from? Where did the gold? Where did all this come from? Well, when those huge, big stars, when they collapsed on themselves, they went not just hydrogen to helium fusion, they went helium to carbon fusion, and carbon to iron fusion. And then beyond iron, those are really, really massive stars. When they finally collapse on themselves, then that's a massive collapse, and that forms these heavier elements. So the heavier elements came from those earlier stars, supernovas. As they died, they left these heavier elements in the space. Okay? I think probably what we ought to do is get the graph up here too. Yeah, this is the protoplanet stage, stage A. Okay? So, yeah, I yell too much at basketball games. Okay, so you had the big collection formed near the center, but it forms this ring a lot like Saturn, isn't it? The big planet in the middle with rings around it. Well, guess what? It's sort of that kind of formation, but this is hot. You've had explosions going out, you know, and it forms this concentration in one region of space, dust, gas, chemical compound. Now, stuff is thrown all around here, too. That would be the Oort cloud, the Kuiper belt, these other things. But the major stuff is formed here, which formed the sun, and the belt around it, that's where the planets form. Concentration, one region of space, of dust, gas, and chemical compounds. Okay? Now, I have a feeling there were multiple of these explosions and things going on. Because at some point, if you think about it, the innermost planets, the four innermost planets, are called the terrestrial planets. They're the densest planets. They have more rocky. Their stuff didn't get thrown out as far. And what's in the outer floor? Gas giants. The gases got thrown way out there. So that's why the ones out here are more gaseous. And guess what? The innermost one doesn't even have an atmosphere. All this gas got blown away. Mercury, no atmosphere at all. And out here, they're all gases. There are some center. The core is made up of other things. So there would be Mercury, Venus, Earth, Mars. Mercury, tiny, no atmosphere, all the gas got blown away. Okay? Maybe it collected around Venus, and that's what made it so extra heavy, dense atmosphere. Earth, thank goodness for plants, we got hydrogen, oxygen and nitrogen, and then poor old Mars out here didn't get as much as a very thin atmosphere, but it does have an atmosphere. But those were your terrestrial planets, the rocky ones, the ones with the heavier elements in them. Okay. I've jumped ahead. All we're talking about here is this phase here. I jumped onto these because I like them, but let's get those up here. Stage B is this one. You have gravitational, your formation of a large rotating nebula that actually looks more like this, okay? The gravitational contraction and the spin rate increases, okay? The sun formed out of this center part, you know, and it spins. The gases and vaporized material, they could be heavy metals too, but they're out here, and as they cool, they tend to spin too. Now, remember we got 4 more out here, big ones, massive things, and in between that, remember, was an asteroid belt. Well, if they started out like this, sort of strung out here, and what we're doing is the gravitational contraction, that's what brings that material back together, spin rate increases and stuff. Most of the mass concentrates on the center protostar. Yeah, we know that. The remaining material forms what they call this accretion disk. Now, it's still hot, gaseous material, but the heavier material is inside, lighter, but it's still not connected, okay? Now, the material in the accretion disk begins clumping. Notice it hasn't clumped yet. It's still thing. Remember there's 4 big, massive other clumps out here too, and there's that belt in between, and what prevents it from clumping, I think, is that huge mass of Jupiter out there that's going around it. When it's trying to get together, Jupiter's pulling it apart. But you see, Jupiter goes at a different rate than it's traveling, so it is an equal opportunity any clump. I mean, it's pulling all the ways. Okay. And then the stage C, the protostar becomes, I don't know why they say it that way. Protosun becomes the sun, or the protostar becomes a star. Why don't they stick with it? But anyway, now the sun is a star. Looks like it was there. It's still in that stage. Now it is. The solar ignition flare-up may have blown the hydrogen and helium atmospheres away from the inner planets, so they wound up on the outer planets. Because there's not that much hydrogen or helium on the inner planets. Okay? The protoplanets are heated, separating the heavy and light materials. The heavy materials going to the core, the lighter materials near the surface, but you have some distribution all the way through. That's why we find some gold near the surface, but not much. Some iron near the surface, more iron than you would find gold, but you even have some heavier stuff near the surface. Other things are happening too. We'll get back to that later. Okay, the protoplanets are heated, separating heavy and light materials. The larger bodies cool slower with the heavy materials settling over longer times in the central cores, and the lighter materials, the silicates and things like that, occurring on the surface, and other things in between, and the gases on the atmosphere. And if there are liquids, they're on the surface, which is where most of our liquids are. Now, if you think about that, what are the odds of having a sun just the right size, not giving off too much radiation, but giving off just enough, but we have just enough atmosphere to prevent us from burning to a crisp because of that radiation, and just the right constitution of that so that the harmful radiation gets out, light gets in, light allows plants to grow, and changes that carbon dioxide into oxygen. Boy, we were really lucky to be right at the right place from the sun, not too hot, not too cold, but just right. And our atmosphere just right, the tilt of the earth just right. Everything had to be really good, otherwise we wouldn't make it. So what are the odds? Well, there are billions upon billions of stars out there. Yeah, there's probably some others that have almost these right conditions too. So maybe there is life somewhere else, or not. We don't know. It's interesting. Okay. So anyway, that's the model. Now they're just showing the 4 inner ones. Remember, there's 4 outer ones too, with those other materials in between. And if Jupiter was big enough to keep those from clumping together like they did here, maybe that's why it's remained a belt. I don't know. I don't know the full physics of what that would have taken, but they suggest that Jupiter was largely responsible. Now, ideas about the solar system. Okay? By the way, back in the 1790s, we knew approximately the distances from the planets to the sun to the planets, at least for the top 7. We didn't know about Neptune yet. We sure knew nothing of Pluto, but it wouldn't have fit anyway. Now, a guy came up with he was an astronomer, a German astronomer named Bode, I think is how you pronounce his name. And he came up with a pattern that fit pretty well. Okay? And this is what they call an empirical model. He came up with a mathematical abstraction that said, hey, when you study these distances, the ones they knew back then, it will fit this formula. And here's what the formula was. The predicted distance from the sun in astronomical units, which is bizarre that he would use that, but he did. The formula was n times 4. No, they got it wrong in the book. It's n plus 4. I thought these aren't right. N plus 4 divided by 10, where n represents where you are, okay? For Mercury, n is 0. Now, you don't have to write this down, but it's in your book. Read it here. N is 0. Then 4 plus 0 is 4 divided by 10. That would be 0.4. Where is Mercury relative to the sun? The book says 0.39. That's pretty close. Assigned to Venus, 3. Okay? 3 plus 4 is 7. Divided by 10, 7/10. Actual distance, 0.72. Hey, pretty good. Okay? Earth, 0, 3, 6. Assign n of 6. N plus 4 is 10. Divided by 10 is 1. Yeah, we're 1 astronomical unit from the sun. Big deal. That's how we define it. We are 1. Okay? Mars, 3, 0, 3, 6, 12. Notice it's doubling each time. 0 to 3 was just 3. Then it doubles every time after that. Mars was 12. 12 plus 4 is 16. Divided by 10 is 1.6. Mars is actually 1.5. Okay? The asteroid belt would be double 12. You get 24. 24 plus 4 is 28. Divided by 10 is 2.8. The actual average distance is probably close to that, but it's the whole belt. It's hard to say. Then Jupiter, double your 24, you become 48. 48 plus 4 is 52. Divided by 10 is 5.2. Where is Jupiter? 5.2. Man, buddy, you're pretty good. Saturn would be double 48 is 96. Plus 4 would be 100. 100 divided by 10 is 10.0. Saturn is 9.5. Man, pretty good. Uranus, double 96, you get 192. Add 4 to it is 196. Divide by 10, you get 19.6. Uranus is 19.2. Really good there. If he had known about Neptune, Neptune would have been 384 plus 4, 388, divided by 10, 38.8. Neptune's only 30. Didn't fit. His model was empirical. He came up with something really nifty, but it only fit the ones he knew. The next one out. So it was an empirical model. It didn't work. But it's pretty interesting how close it got. All right, another mistakes and misunderstanding. This book has lots of blurbs like this. UFOs and You, that talks about 3 things: natural phenomena, aliens, and psychological factors. 1 and 3 are more likely. Okay, the aliens, not likely, but you can't rule them out. Okay, it's worth a read. Please read your book. All right, now we're into ideas about the solar system. Those were the end things before. All right. Go back in history when we had it all wrong. We thought the Earth, geography, was the center of the universe. And it sure seems to fit pretty well. The sun went around us. The moon goes around us. The planets kind of went around us. The stars all went around us. Hey, we must be the center of the universe, right? It seemed to fit most of the data, and it was an attempt of the early Greek astronomers and philosophers to explain those strange motions. The stars were very regular. The sun was very regular. The moon was regular, but in a slightly different way. But those planets, boy, they blew everything. They sort of were regular, but not completely. But this placed the Earth at the center of the orbits of the planets. The exceptions for this model, the planets mostly, but the moon somewhatly and the other things some. Exceptions were explained by, I think he was Egyptian, named Ptolemy. The P, I think, is silent. Ptolemy, and it's called the Ptolemaic system. He tried to explain those exceptions. But the inconsistencies that were there grew in number and became much more complicated to explain. And finally they said, man, this just doesn't work. Okay? Now, why did we hang on to it so long? Well, I hate to say this, but the church was involved. And the church, being made up of humans, they tried to take some little obscure scriptures and twist them to mean we were the center of everything, when it really, that wasn't what it meant. But everything else fit. The church said, no, we've got to be the center. Well, along came the heliocentric model. Helio meaning the sun. Oh, that's very, one reason the church probably didn't like it. Helios or something like that was probably an Egyptian god or something like that they didn't want to have anything to do with. But anyway, it was called the heliocentric, the sun being the center. Then the idea that the earth revolved around the sun, that came from Copernicus. Now, lucky for Copernicus, he lived way up here. What did I do with my globe? Did I leave it in the other? I thought I brought it in here. I guess I did. Let me see if I can disrupt it. Okay, as I was saying, kind of lucky for Copernicus that he lived up here in Poland. And the center of the church, of course, was down here in Italy, Rome, okay? So he was sort of out of the range of the church. They couldn't quite get to him. So he had a little more freedom up there to come up with these things. About 1543, he suggested this. Of course, they were ready to bury him, okay? But he was way up there, sort of safe. But then, poor old Galileo. Poor old Galileo, well, he made this telescope, was able to see Jupiter spinning, Jupiter not being a star, but unlike a star, actually had a shape, and it spun. The Earth, the Sun, they already knew spun. Jupiter spins. Guess what? If the Earth spins, that would account for all the motion that we've been thinking everything went around us, when actually we're the ones turning. And if you did that, and then he also saw these moons going around Jupiter, and if the moons could go around Jupiter, and our moon could go around us, that means we could go around the sun. And that explained a lot. Okay? But the poor old Galileo, he lived down here in Pisa, Italy. Not too far from Rome, okay? So therefore, he almost got, if he hadn't been such a great scientist,
They would have let him off.
yeah. But they let him go with just house arrest. And they kept him there. He continued writing and studying, saying, yeah, I believe you, writing, I don't believe him, I don't believe him. And he recanted everything he had done, and they found that after his death. But anyway, that supported him. Now, much later, here came a guy named Kepler. I'm trying to remember where Kepler was from. Germany, maybe? But he came up with some laws about planetary motion. 3 laws of planetary motion. And these laws were, again, empirical laws based on his observations and his calculations, and they described things really well, but he didn't know why. And he called on this other little scientist named Isaac Newton and said, hey, Isaac, can you tell me why this would be the case? So Newton had to develop, not necessarily in this order, laws of motion, the 3 laws of motion, laws of gravity, which would contribute to this. But before he could do any of that, he had to have a whole new mathematics, because the math at his time just could not handle these things, so he developed calculus. So one guy changed all of physics and all of math in just a few short years. Pretty sharp dude, okay? And this is how all this fits together. So Kepler's laws further explain the heliocentric model. But here was the problem. Here was the problem way back with the Greeks and everyone else. Stars move very regularly around the Earth. The sun moved regularly in a different pattern, but did move around the Earth. The moon moved in a very regular pattern around the Earth. They finally got one right. It does go around the Earth. Okay, but the planets, oh my word, what is wrong with those things? In fact, the word planet came from the word, I think Greek word, wanderer. Because it wouldn't stay on track. It just sort of drifted. Here's what was happening. Here is the orbit of the Earth, and here is the orbit of Mars. And if you go back and check and count the annual rate of Earth around Mars, of the Sun, annual rate of Mars around the Sun, this is how things look. So let's pick us at number 1 here. Mars happened to be here. Well, in the sky, Mars was right there, because looking up from us, that's where Mars was. Sometime later, I don't know when this was exactly, if this all the way around is 365 days, what's that? Maybe a week or 2. We're over here now, and Mars has moved here. So Mars in the sky moved from here to here. Good Mars, you're following a good pattern. Good Mars, good Mars. And then we become here, and Mars is there, and it's still following a pretty good pattern. Then on period 4, we're over here. It looks like a little longer period. We're here. Mars has moved over to here. So it's here. Not great, but it's still a pretty good pattern. Then we are up here, and Mars is here, and now it's here. Mars has been tracking across the sky like this, and then has doubled back on itself and is going in the opposite direction. Mars, what's your problem here? You're supposed to be going that way. Okay? Then when we're over here at number 6, Mars is here at 6, so at 6 is still going the wrong way. And when we're here at 7, Mars is here at 7. I think I got this wrong. God, it's here at 7. And it's turned around and it's going back in the right direction again. You're wandering around, planet, okay? It's just sort of drifting through space. The stars didn't do this. The sun didn't do this. The moon doesn't do this. Only these pesky planets that do this. Mars being one of the worst, it does this. So it was named a planet, meaning a wanderer. If you were trying to have this Earth as the center of the universe, Mars is doing like this, how do you explain that? It's hard to do. But when you put it, Earth going around the sun and Mars going around the sun, then yeah, that makes sense. Because they line up differently at different times of the year. Yeah, that makes some sense. So the heliocentric model explained these things that Ptolemy and all the others and all their complicated gyrations of trying to get it to work just could not get it. Heliocentric model like that works nicely. Accounts for changes of speed, changes of direction. Yeah, this is what happened. Okay? And Kepler then refined things big time, and then with the help of Newton, actually explained it. That's the last slide in the text. It's not the last thing in the text. They have what is, to me, a really, well, they go into Kepler's law. It was one little line on there. They define Kepler's first law, states that each planet, moves in an orbit that has the shape of an ellipse. Now, you know what an ellipse is? It's sort of, not quite egg-shaped, but sort of like that. It's not circular, but elliptical.
It's like almost an oval, but not quite.
Yeah. Now, you can be really long ellipses or almost circular ellipses. Every planet follows an elliptical pattern. Some are almost circular and some are a bit more elongated. What it is, you have 2 points in there. A circle has one center, and every point on the circle is equal distance from that center. What an ellipse is, picture having a string that you connect to each end here, and then take a pencil and go as far from those as you can. That forms an ellipse. If those 2 points are on top of each other, you have a circle. If they're a little bit apart, you have almost a circle, slight elongation, far apart, really long. Now, there is no planet that has this elliptical of an orbit. Nowhere close. But the comets, they are very much like this. Pluto, far more like this than the planets. Okay? Now, so, his first law says, each planet moves in an orbit that has the shape of an ellipse with the sun located at one of those 2 foci. Those 2 points are called the focus. One would be a focus, 2 are foci. Those are the 2 foci. The sun is at one of the focus. One focus. That's the first law. The second law states that, wish these were on the slides, but they're in your book. Second law states that an imaginary line between the sun and the planet sweeps out, okay, moves across equal areas of the ellipse during equal time intervals. What does that mean? When you're close to the sun, the planet is moving rapidly. So in one time interval, it's going to go pretty far, but it's close to the sun, so it's going to trace out the area of a sector here. Okay, when it's further from the sun, then in the same time period, it goes very, very short distance. But because it's further from the sun, that sector is going to have the same area as this one did. Okay? So, that's the second law. States that an imaginary line between the sun and the planet moves over equal areas of the ellipse during equal time intervals. Okay? Meaning the orbital velocity is fastest when you're closest to the sun, slowest when you're further from the sun. That's what you get. Okay? Now, a couple of words that you might need to know, especially if you're ever on Jeopardy or something. The point at which the orbit comes closest to the sun is called the perihelion. Helion means sun, Helion. That's a derivative of the word for sun, helios. And peri, I guess, means close. But the point where it's farthest from the sun, opposite side of the other focus, that would be the aphelion. The aphelion. The root's the same, helion, but it's AP for the farthest, PERI for the closest. Aphelion. Okay. Now, these are just words. That's the second law. Sweeps the same area in the same time. The third law, this is a weird one, states that the square of the period of the planet's motion, in other words, the time it takes to go one complete revolution around the sun, the square of the period of the planet's motion is proportional to the cube of the planet's semi-major axis. Okay, the major axis is the one that's long way, the semi-major axis is the short axis. Okay, the cube of the short axis. Okay, the square of the period is proportional to the cube of the semi-major axis. All right. Now, we had Bode's law. It looked like it came close to fitting. But now if we do, using Kepler's third law, that relationship between the square of the period and the distance, the cube of the semi-major axis, and if you plot the planets now, where the periods are on the vertical axis, and you use a log scale that accounts for squaring and cubing and stuff, the distances in astronomical units also on a log scale. Look at that. Every planet, including Neptune, falls on a perfectly straight line on a log scale, indicating the equality of different powers. Okay? And boy, do they fit perfectly. And if there was a planet in between Mars and Jupiter, it would fall right on that scale as well. Okay? But there's not. That's on around page 400. Now he has a slightly different book.
It'll be $3.99.
$3.99. It's pretty close. Okay? Now, the next page, 401 in my book, or probably 400 in yours, is People Behind the Science. Gerard Peter Kuiper. Dutch-born, but moved to the U.S. astronomer, best known for his studies of, well, the Kuiper belt was named after him. Many things he studied, but he actually was better known for his studies of lunar and planetary surface features and his theoretical work on the origin of the planets, but they named the comet belt after him. So there's Kuiper. He lived in the 20th century, 1905 to 1973. Now, if you choose to write your paper on Kuiper, this can give you the idea, but this cannot be your source. Your source has to come from outside the book. Library, internet, okay? You can get ideas from here, but you can't use this as your source, okay? And there's a lot of things mentioned here. He also discovered the second moon of Neptune, the fifth moon of Uranus. So there's a lot of things he did besides having the comment belt named after him. Doesn't sound like he really did that much for comments. They just named the belt after him, but we want such an incredible science. Okay. Now we've gotten ourselves into the dilemma. Thank you very much. Finishing 2 chapters, meaning we technically should have both tests on Thursday.
But I have a question about the first test.
Okay.
I don't know what's going to be.
Okay.
Or do I just read the entire chapter?
Read the chapter is the very best thing. Look at the first 2 YouTube videos, because that's where I go over it. Okay? And you've gotten all of today's pretty much. When you read the chapters, I said this before, I'll say it every chapter, read them, I'd say a couple or 3 times if you need to understand it well. Once you've read them, the summary does summarize, but it doesn't get it all. But it's a pretty good thing of the important issues. Then there's key terms. If you know basically their meanings, they're listed alphabetically, but they give the page number where they're first introduced or defined. So those are in the text too, around page 403 or so. But then I think the very best thing are the applying the concepts. These are multiple choice questions, and most of your questions on your test are going to be multiple choice. Maybe all, I don't remember on this test or not. You won't have 41, they have 41 in the book, you're going to have closer to 20. They're not going to be the same questions, but they'll be testing the same content, just asked in different ways. So if you can get these right, they have the answers here. 41 is a little bit fewer than we had for chapter 1, but that's a great thing to study for both of your tests. Questions for thought, they have 11 here, the first chapter had, they have 19 here, about like the first chapter. 6 for further analysis, and then they have some other things, like the parallel exercises, which are a bit more numerical, but we've been sort of skipping those because the math involved with them is a little beyond, and the physics involved with them was covered in the first half of the book, and we haven't covered the first half of the book. So I haven't been, but you might want to look at those just for fun. So what are we going to do next time? Okay?
Oh,
Okay.
our notes allowed?
What's that?
Our notes allowed?
Yes, you can have a formula and equation sheet for every test, including the final. Anything you want to write down on a piece of paper, front and back, as small or as big as you want to write it, you can bring with you to the test.
With anything?
Anything you want to put, anything you think may be important. And I think
A
these
single
things like
sheet.
the summary,
That's for
the
each
terms,
chapter, right?
Huh?
That's for each chapter.
Each chapter you do, right? Okay. Now, so what will we do next time? We have 4.5 hours together, don't we? The last half hour will be your test on chapter 15. That will be 4:30 to 5. From 4 to 4:30 will be the test on chapter 14. Thank you very much. Okay. The 2 hours before that, that would be from 2 to 4. I got that right, yeah. 2 to 4 will be our lab on chapter 15. So from 1 to 2:30, no, 12:30 to 2, 12:30 to 2, an hour and a half there. If you have any questions on either chapter, especially if you've done those applying the concepts, and you consistently cannot see how they got the answer they give as the answer for that question, ask me. We'll go over it as a group, and either we'll find out they made a mistake or I'll clear it up. Yeah.
Just need to email you if we're not.
I'm sorry.
Just need to email you if we're not going to be here Thursday to reschedule the test.
Okay. You mean if the whole group won't be here? Oh, you won't be here. Yeah. You can come anytime during my office hours and retake the test. Listen to the YouTube because I'll try to get the lab on YouTube as well. So it's going to be a little bit of delay there. So for that first hour and a half, we will answer any questions you have. Then we'll start chapter 16. Won't get very far, but we'll get a little ways on 16. Good deal. I think it must be time to go.
Absolutely.
Oh, okay. All right, good deal. Thank you. All right, another paper topic. Let's get them in, folks. Okay, I hope all that recorded, because I was a little far from the... Okay, thanks. All right, what's that? All right, a lab, excellent.
Is it just 14 on Thursday or 14 and 15?
14 and 15.
They're being
14,
tested on.
yeah,
Okay.
two separate tests,
Okay,
though,
that's
okay? And, I'm sorry? Yeah, you can bring notes for both chapters. 1 page of notes for both chapters. For each chapter, is what I'm trying to say. Here. Okay. Good deal. It's making sense?
Yeah.
You seem to be staying right on top of it, so good deal.
Oh, see, I used to go to UAB, but I had some trouble, and so I transferred here until I got to grasp things a little better.
Right.
And I took an astronomy class at UAB.
Oh, so this is old hat to you.
Well, no, it was actually a different biology. It was
Right.
actually about the possibility of life on other planets.
Yeah,
So
okay.
it was a little more advanced.
Biological than this. This is
Yeah.
more physical. Right. All right, well, good
But
deal.
I do remember some of the concepts.
Right.
And
Well, I
also
appreciate your
some
questions
of the graphical
and
labs.
contributions, because you're contributing better than anyone else in the class, so way to go.
Since I can't write, I always try to.
Think.
Yeah.
Right. Yeah. Good deal. Sorry we have to move you around, but they had a lab
It's okay.
thing coming in there.
Keeps me from falling asleep, honestly.
Yeah,
By
I
this
guess
point,
so.
I'm very tired.
All right. We'll see you Thursday then.
Alright, see you Thursday.
All righty. Oops, I recorded all that, sorry.